You think you know how the universe began? Let me tell you something that's going to blow your mind. Everything you've been taught about the Big Bang might be completely wrong, or at least massively incomplete. Wait, before you click away, stay with me for the next 30 seconds, because what I'm about to reveal is going to literally flip your understanding of reality upside down. Picture this. You're in absolute darkness. Not the darkness of your bedroom at night. Not the darkness when you close your eyes. I'm talking about a darkness so complete, so absolute, that the concept of darkness itself doesn't even exist yet. No space, no time, no matter, no energy, nothing. And then, in an instant that wasn't even an instant because time didn't exist, bang. That's the story we've all been told, right? The Big Bang created everything. Case closed. Science has spoken. But here's where things get absolutely insane. And this is where you need to pay attention, because this changes everything. What if I told you that some of the greatest minds in physics today are seriously questioning whether the Big Bang actually created the universe at all? Yeah, you heard that right. And we're not talking about random conspiracy theorists in their basements. We're talking about Nobel Prize winners, Oxford professors, and researchers at CERN who are looking at the data and saying, wait a minute, something doesn't add up here. Now, before we dive deep into this rabbit hole that goes way deeper than you can imagine, let me tell you what we're going to cover in this video. We're going to dismantle everything you thought you knew about the beginning of the universe. We're going to explore the Big Bang Theory and its problems, massive problems that most people never hear about. Then we're going to venture into alternative theories that sound like they're straight out of science fiction, but are actually being seriously considered by top scientists. We're talking about simulated universes, cyclical cosmology, quantum fluctuations. And yes, we'll even tackle the big question, the elephant in the room. Could there be something beyond science that created all of this? This isn't just another science video. This is about the most fundamental question humanity has ever asked. Where did everything come from? And trust me, by the end of this video, your perspective on existence itself will never be the same. So buckle up, because we're about to embark on a journey from the very edge of scientific knowledge into territories that will make you question reality itself. Let's get into it. Part 1. The Big Bang Theory. What we're told. Chapter 1. The standard story. All right, let's start with what you probably learned in school, the version of events that's been drilled into our heads since we were kids. The Big Bang Theory, the cornerstone of modern cosmology, the scientific consensus. But here's the thing, and pay attention to this because it's crucial. Understanding what the Big Bang Theory actually says is the first step to understanding why it might be wrong. So let's rewind. Not just to yesterday or last year, but to 13.8 billion years ago. Actually, let's go even further back than that. Let's go to the very beginning. Time 0. T equals 0, as physicists like to say. Here's what the standard Big Bang Theory tells us. The universe began as an infinitely small, infinitely dense, infinitely hot point. Scientists call this a singularity, which is basically a fancy way of saying, we don't really know what the hell this is, but the math breaks down here. Everything that exists now, everything, was compressed into a space smaller than an atom. Actually, smaller than a proton. Actually, the theory suggests it was a point of literally zero size. Wrap your head around that for a second. All the matter in all the galaxies, all the energy, all the space itself, crushed into something with no dimension. And the temperature? We're talking about temperatures so extreme that we don't even have proper ways to describe them. Billions upon billions of degrees. Temperatures where the fundamental laws of physics as we understand them completely fall apart. And then suddenly, this singularity started expanding. Not exploding into pre-existing space, and this is where most people get it wrong, but space itself began expanding. The universe didn't expand into anything. The universe is everything, and it started growing from this impossibly small point. In the first fraction of a second, and we're talking about time intervals so small they make a nanosecond look like an eternity. The universe underwent what scientists call inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor larger than you can imagine. We're talking about going from smaller than an atom to bigger than a galaxy in less time than it takes light to cross a single proton. This sounds absolutely insane, right? And yet, this is what the equations tell us. This is what fits the data we observe. Or does it? We'll get to that. As the universe expanded, it cooled down. Think about how a compressed gas heats up and an expanding gas cools down. Same principle, just on a cosmic scale. Within the first second, and yes, we're now measuring time in actual seconds, the universe had cooled enough for the fundamental forces to separate out. See, in those earliest moments, all the forces we know today, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, they were all unified into one superforce. But as things cooled, they split apart like oil separating from water. Within the first 3 minutes, the universe had cooled enough for the first atomic nuclei to form. Mostly hydrogen, some helium, tiny amounts of lithium. These are the simplest elements, the building blocks that would eventually form stars, planets, and us. But here's something wild. For the next 380,000 years, the universe was completely opaque. You couldn't see anything. Light couldn't travel freely because the universe was filled with this dense fog of plasma, electrons and nuclei bouncing around, scattering photons in every direction. It was like trying to see through a cloud, but the cloud was literally everywhere. Then, 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons got captured by nuclei, and suddenly, light could travel freely. Scientists call this recombination, and the light from this era is what we detect today as the cosmic microwave background radiation. It's literally the afterglow of the Big Bang, and it's everywhere you look in the sky. Over millions and billions of years, gravity did its thing. Those tiny variations in density in the early universe, places that were just slightly more dense than others, started pulling in more matter. These became the seeds of galaxies. Stars formed, lived, and died. Heavier elements were forged in stellar furnaces and scattered across the cosmos when massive stars exploded as supernovas. Second and third generation stars formed from this enriched material. Planets formed, and on at least one planet, around an unremarkable star in an unremarkable galaxy, something extraordinary happened. Life emerged and eventually started asking questions about where it all came from. That's the story. That's what we're told. And for decades, this narrative has been incredibly successful at explaining a huge range of observations. It's elegant. It's comprehensive. It fits the data, mostly. But here's where things get interesting, and this is where you really need to pay attention. Chapter 2. The evidence that made us believers. Before we tear this theory apart, and trust me, we're going to tear into it hard, we need to understand why scientists believed in the Big Bang in the first place. Because contrary to what some people think, scientists didn't just make this up. There's actual evidence, compelling evidence, that led the scientific community to accept this wild idea that the universe exploded into existence from a tiny point. Let's talk about the first major piece of evidence, and this is the one that started it all: the expansion of the universe. In the 1920s, an astronomer named Edwin Hubble, the guy the telescope is named after, made an observation that would change everything. He was looking at distant galaxies, measuring their light, and he noticed something absolutely bizarre. The light from these galaxies was shifted toward the red end of the spectrum. This is called redshift, and it happens because of the Doppler effect, the same effect that makes an ambulance siren sound different as it moves toward or away from you. But here's the kicker. The farther away a galaxy was, the more its light was redshifted. This could only mean one thing. These galaxies were moving away from us. And not just moving away randomly, but the farther away they were, the faster they were receding. This is Hubble's law, and it was absolutely revolutionary. Think about what this means. If everything is moving away from everything else, and the farther apart things are, the faster they're separating, then if you run the clock backward, everything must have been closer together in the past. Keep running it backward, and you get to a point where everything was in the same place. The Big Bang? This was the first domino to fall. But it wasn't enough on its own. Scientists needed more evidence. Enter the cosmic microwave background radiation, or CMB. This is probably the most important piece of evidence for the Big Bang, and its discovery is one of the greatest stories in science. In 1964, two scientists named Arno Penzias and Robert Wilson were working with a sensitive radio antenna at Bell Labs in New Jersey. They were trying to measure radio signals from space, but they kept detecting this annoying background noise. It was coming from everywhere, all directions, at all times. They even thought it might be pigeon droppings interfering with their antenna. I'm not kidding, they actually cleaned bird poop off their equipment trying to get rid of this signal. But the signal remained, and here's what blew everyone's minds. This signal was exactly what physicists had predicted should exist if the Big Bang theory was correct. Remember that opaque phase of the universe I mentioned earlier, when atoms formed and light could finally travel freely? That light has been traveling through space ever since, getting stretched and cooled by the expansion of the universe. Today, that ancient light appears as microwave radiation at a temperature of about 2.7 degrees above absolute zero. And it's everywhere. Point your detector at any spot in the sky, and you'll detect it. It's the oldest light in the universe, a snapshot of what the cosmos looked like 380,000 years after the Big Bang. Penzias and Wilson won the Afterwort Nobel Prize for this discovery, and rightfully so. It was smoking gun evidence for the Big Bang. But wait, there's more. The third major piece of evidence is the abundance of light elements in the universe. According to Big Bang nucleosynthesis theory, during those first few minutes after the Big Bang, when the universe was still incredibly hot and dense, nuclear fusion reactions should have created specific amounts of hydrogen, helium, and lithium. And here's the amazing part. When we look at the universe, at the oldest stars, and the most pristine gas clouds, we find exactly the ratios of these elements that the Big Bang theory predicts. About 75% hydrogen, 25% helium, with trace amounts of lithium. This can't be explained by stellar fusion alone. Stars make heavier elements, sure, but they can't account for the specific ratios we observe of these light elements. The Big Bang theory, on the other hand, predicts these ratios with stunning accuracy. It's like finding a murder weapon with the suspect's fingerprints all over it. And there's a fourth piece of evidence that's more recent but equally compelling: the large-scale structure of the universe. When we map out where galaxies are in the universe, we don't see them distributed randomly. They form this incredible cosmic web with filaments of galaxies separated by vast voids. And guess what? When scientists run computer simulations starting with the tiny density fluctuations we see in the cosmic microwave background and letting them evolve according to the laws of physics and the Big Bang model, they get structures that look remarkably similar to what we actually observe. So you can see why the Big Bang theory became the dominant paradigm. It's not just one piece of evidence. It's multiple, independent lines of evidence all pointing to the same conclusion: the expansion of the universe, the cosmic microwave background, the abundance of light elements, the large-scale structure. All of these fit beautifully with the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. For decades, it seemed like case closed. The Big Bang happened. We figured it out. Pop the champagne, give out the Nobel Prizes, write it in the textbooks. But science doesn't work that way. Science is about constantly questioning, constantly testing, constantly looking for holes in even our most cherished theories. And when scientists started looking closer at the Big Bang theory, they found holes. Big holes. Holes so big that some scientists are now wondering if we've been wrong about the whole thing from the start. And that's where things get really interesting. Chapter 3: The Cracks in the Foundation. Okay, here's where we need to talk about the problems, the issues, the things that keep cosmologists up at night. Because despite all that compelling evidence I just laid out, the Big Bang theory has some serious, and I mean serious, problems that most people never hear about. Let's start with the most obvious one. What caused the Big Bang? Think about it. The Big Bang theory does an amazing job of describing what happened after the initial moment of expansion. But it has absolutely nothing to say about what caused that expansion in the first place. What made the singularity suddenly start expanding? What was there before? These are questions that the theory simply cannot answer. Some physicists wave their hands and say, well, there was no before because time itself began with the Big Bang. Okay, fine, but that doesn't actually answer the question. It just reframes it. Why did time begin? What triggered the existence of the singularity? What set the initial conditions? The Big Bang theory is silent on these questions. It's like having a detailed explanation of how a car works, but having no idea why the car exists in the first place or who built it. But this is just the beginning. Let's talk about the horizon problem, and this one's a real head-scratcher. When we look at the cosmic microwave background radiation, we see that it's incredibly uniform. The temperature is the same in all directions to within 1 part in 100,000. That's absurdly uniform. But here's the problem. According to the standard Big Bang model, regions of the universe that are on opposite sides of the sky should never have been in contact with each other. They're too far apart. Light hasn't had enough time since the Big Bang to travel between them. So how did they end up at the same temperature? Imagine you have 2 pots of water in separate rooms that have never been connected, and somehow they're both at exactly 72.3 degrees. That doesn't make sense unless there was some way for them to have been in thermal contact at some point. But according to the basic Big Bang model, that contact never happened. This is called the horizon problem, and it's a massive issue. For the universe to be as uniform as we observe, different regions would have needed to be in causal contact, meaning they could have exchanged information and energy. But the math says they never were. The standard solution to this problem is cosmic inflation, that incredibly rapid expansion I mentioned earlier. The idea is that if the universe expanded fast enough in the earliest moments, then regions that are now separated could have been in contact before inflation blew them apart. Problem solved, right? Not so fast. Inflation solves the horizon problem, sure, but it introduces its own set of questions and problems. What caused inflation? What is the inflaton field that drove it? Why did inflation start? Why did it stop? And here's the real kicker. We have no direct evidence that inflation actually happened. It's a theoretical patch to fix a problem with another theory. It works mathematically, but we're essentially solving one mystery by proposing another mystery. Now let's talk about the flatness problem, and this one might be even weirder. When we measure the geometry of the universe, we find that it's flat, or at least very close to flat. What does flat mean in this context? It means that if you draw a triangle in space with laser beams, the angles add up to exactly 180 degrees, just like in the geometry you learned in school. The universe could have been curved, either positively like a sphere or negatively like a saddle, but it's not. It's flat. Here's why that's bizarre. For the universe to be flat today, the density of matter and energy in the early universe had to be tuned to an incredibly precise value. We're talking about precision to dozens of decimal places. If the density had been even slightly higher, the universe would have collapsed back on itself in a big crunch billions of years ago. If it had been slightly lower, the universe would have expanded so fast that galaxies could never have formed. It's like balancing a pencil perfectly on its tip. Technically possible, but why? What set the initial conditions so precisely? The odds against this happening by chance are astronomical, literally astronomical. Again, inflation is proposed as a solution. The idea is that inflation smoothed out the universe and drove it toward flatness, regardless of what it looked like before. But again, we're solving one mystery with another mystery. And then there's dark matter and dark energy. And oh boy, this is where things get really wild. When scientists calculate how much normal matter, the stuff made of atoms, is in the universe based on Big Bang nucleosynthesis, they get a number. But when they look at how galaxies rotate and how galaxy clusters move, the amount of gravity they observe requires way more mass than the visible matter can account for, like 5 times more. So scientists invented dark matter. It's matter that doesn't interact with light, which is why we can't see it, but it does have gravity. And apparently, it makes up about 85% of all matter in the universe. We can't see it, we can't detect it directly. We don't know what it's made of, but we need it for the theory to work. And dark energy is even crazier. In the late 1990s, scientists discovered that the expansion of the universe is not just continuing, it's accelerating. Galaxies are flying apart faster and faster. This should not be happening if gravity is the dominant force on cosmic scales. Something is pushing the universe apart, something we can't see or detect directly. Scientists call it dark energy, and it apparently makes up about 68% of the total energy content of the universe. Let me repeat that. We can only see and account for about 5% of what's actually in the universe according to the Big Bang model. The other 95% is stuff we've never directly detected and don't understand. Dark matter, dark energy. We've invented these concepts to make the observations fit the theory. Now, to be fair, there is evidence for both dark matter and dark energy beyond just we need them for the math to work. We see gravitational lensing effects that suggest invisible mass. We see the universe's expansion accelerating, but the fact remains that we're building our entire understanding of cosmic origins on a foundation where 95% of the ingredients are complete mysteries. That's like trying to bake a cake when you only know what 5% of the ingredients are. Sure, you know there's flour in there, but what's the other 95%? Mystery spices? Unicorn tears? You have no idea, but you're confident you know how the cake was baked. And here's another problem that doesn't get talked about enough: the singularity itself. The Big Bang Theory says the universe started from a singularity, a point of infinite density and infinite temperature. But here's the thing: whenever infinities show up in physics, it's usually a sign that your theory has broken down. It's a red flag that you're pushing your equations beyond where they're valid. General relativity, Einstein's theory of gravity that underlies the Big Bang model, predicts this initial singularity. But general relativity also breaks down at the quantum scale, and a singularity is definitely quantum scale. We need a theory of quantum gravity to properly describe what happens at the singularity, and we don't have one. String theory, loop quantum gravity, these are attempts, but we're nowhere close to a complete, tested theory. So the Big Bang Theory is trying to describe the origin of the universe using physics that we know doesn't work under those conditions. It's like trying to use Newtonian mechanics to describe what happens inside a black hole. You're going to get nonsense. And let's not forget about the measurement problem. Recent observations have revealed what scientists are calling the Hubble tension. When we measure the expansion rate of the universe using the cosmic microwave background, we get one number. When we measure it using supernovas and other local methods, we get a different number. And these numbers don't agree. They're off by enough that it can't just be measurement error. This might not sound like a big deal, but it's huge. It suggests that either our measurements are wrong in ways we don't understand, or our model of cosmic evolution is incomplete. Maybe the universe didn't expand at a constant rate. Maybe dark energy has changed over time. Maybe we're missing something fundamental. Some scientists are even proposing that we might need to throw out parts of the Big Bang model entirely to resolve this tension. So let's take stock of where we are. The Big Bang theory has impressive evidence supporting it, sure. But it also has the horizon problem, the flatness problem, the singularity problem, the what came before problem, the dark matter mystery, the dark energy mystery, and now measurement inconsistencies that don't add up. It's starting to look less like a solid foundation and more like a theory held together with duct tape and theoretical patches. And this is where some scientists are starting to ask a very uncomfortable question. What if we've been looking at this all wrong? What if the Big Bang wasn't the beginning at all? What if there are other explanations, other theories that might do a better job of explaining where the universe came from? That's exactly what we're going to explore next. And trust me, some of these alternative ideas are going to make the Big Bang look conservative by comparison. Part 2. Alternative Cosmologies. Chapter 4, Before the Bang, Cyclical Universe Models. All right, let's dive into the alternatives. And we're going to start with an idea that's actually ancient, but has been revived in modern physics with some fascinating twists: the cyclical universe. Here's the basic concept. What if the Big Bang wasn't the beginning of everything, but just the beginning of this particular phase of the universe? What if the universe goes through cycles of expansion and contraction? Big bangs followed by big crunches over and over eternally? Think about it like breathing. You breathe in, you breathe out. Expansion, contraction. What if the universe does the same thing? Our Big Bang was just the universe breathing in, and eventually it'll breathe out, contract back down, and then breathe in again with another Big Bang. This idea has been around for thousands of years in various forms. Hindu cosmology talks about cycles of creation and destruction spanning billions of years. Ancient Greek philosophers played with similar concepts. But now, modern physicists are taking this ancient idea and giving it a rigorous mathematical foundation. One of the most intriguing modern versions is called the ekpyrotic universe model, developed by physicists Paul Steinhardt and Neil Turok. Their idea is based on string theory and involves extra dimensions. Yeah, we're going there. In their model, our universe is a three-dimensional brane, short for membrane, floating in a higher dimensional space. There are other branes out there, parallel universes, if you will, also floating in this higher dimensional space. And every once in a while, these branes collide. When they collide, bang. That collision is what we experience as the Big Bang. The collision creates a tremendous amount of energy. Matter springs into existence, and the universe begins expanding. But here's the twist. After the collision, the branes bounce apart. They separate, drift through the higher dimensional space, and eventually, trillions of years from now, they'll collide again. Another Big Bang, another cycle. This model is wild, but here's why some scientists take it seriously. It solves several of the problems with the standard Big Bang model. The horizon problem? Solved, because the branes were in contact during the previous cycle, so different regions of the universe could have equilibrated before the collision that created our current cycle. The flatness problem? Also solved, because the collision process naturally produces a flat universe. And there's no singularity problem, at least not in the same way. The collision is violent, sure, but it's not infinitely dense. The physics doesn't break down in quite the same way, but cyclical models face their own challenges. One big issue is entropy. The second law of thermodynamics says that entropy, disorder, always increases. So if the universe goes through cycle after cycle, shouldn't entropy just keep building up until eventually the universe reaches maximum entropy and can't cycle anymore? This is called the entropy problem for cyclical models, and it's a serious objection. Some physicists have proposed solutions. Maybe entropy is reset somehow during the contraction phase. Maybe there's some mechanism we don't understand that allows disorder to decrease. But these are speculative answers to a very real problem. Another challenge, we see the universe accelerating in its expansion, driven by dark energy. If this acceleration continues, the universe will never collapse back down. It'll just keep expanding faster and faster forever. So how do you get a cyclical model to work when the universe seems hell-bent on expanding eternally? Steinhardt and others have proposed that the properties of dark energy might change over time. Maybe what's driving acceleration now will reverse in the distant future. Maybe. But that's adding another layer of speculation to an already speculative model. Despite these challenges, cyclical models remain attractive to many physicists because they avoid the awkward question of what was before the Big Bang. There was no before. There have always been cycles. The universe is eternal, just changing form. But let's move on to another alternative that's even more mind-bending. Chapter 5, Quantum Creation, the universe from nothing. Now we're going to talk about something that sounds completely insane, but is actually taken very seriously by theoretical physicists. The idea that the universe literally came from nothing, not from a tiny something, not from a singularity, from absolute, complete nothingness. Before you click away thinking I've lost my mind, let me explain what physicists mean by nothing, because it's not what you think. In quantum mechanics, and this is crucial, nothing is not a stable state. The vacuum of space, what we think of as empty space, is actually seething with activity at the quantum level. Virtual particles are constantly popping into and out of existence. Particle-antiparticle pairs appear, exist for a fleeting instant, and then annihilate each other. This isn't speculation, we've observed this. The Casimir effect, Hawking radiation from black holes, these are real phenomena that demonstrate that quantum nothingness is actually quite something. Now, here's where it gets wild. Physicist Lawrence Krauss and others have proposed that the entire universe could be a quantum fluctuation. Just like those virtual particles that pop into existence in empty space, maybe the entire universe popped into existence from the quantum vacuum. Think about that. No God needed. No pre-existing conditions needed. Just the laws of quantum mechanics. And boom, universe. But wait, you might be thinking, doesn't that violate conservation of energy? You can't just create something from nothing, right? Well, here's the crazy part. The total energy of the universe might actually be zero. Stay with me here. Matter and radiation have positive energy, but gravity has negative energy. When you add up all the positive energy from matter and all the negative energy from gravity, some calculations suggest they might exactly cancel out. The universe could have a total energy of precisely zero. If that's true, then creating a universe doesn't violate energy conservation. You're not creating something from nothing. You're creating a perfectly balanced combination of positive and negative that adds up to the same nothing you started with. It's like borrowing $100 from one bank to immediately deposit in another bank. Your net wealth hasn't changed. You're still at zero, but you've created a transaction. This is mind-blowing stuff, but it has problems, big problems. First, where do the laws of quantum mechanics come from? If you're saying the universe popped into existence because of quantum fluctuations, you're assuming quantum mechanics already exists. But quantum mechanics is a set of laws that describe how things behave. Where did those laws come from if there was nothing before the universe? It's like saying a building constructed itself because of the laws of architecture. Okay, but where did the laws of architecture come from? You're just pushing the question back one step. Second, even if quantum fluctuations can create particle-antiparticle pairs that exist for tiny fractions of a second, how do you get from that to an entire universe that lasts for billions of years? The time scales and energy scales are incomparable. It's like saying that because you can make a small ripple in a pond by dropping a pebble, therefore the entire Pacific Ocean could spontaneously appear. The jump in scale is absurd. Krauss and others argue that in the early quantum state, time might not even be well defined, so asking how long a quantum fluctuation can last doesn't make sense. Maybe, but that's getting pretty hand-wavy. Third, and this is a philosophical point that really bothers some people, even a quantum vacuum isn't nothing. It's something. It's a state with properties, with quantum fields, with potential. If you need a quantum vacuum to start with, you haven't explained where everything came from. You've just labeled the pre-universe state differently. Despite these objections, the quantum creation model is attractive because it's testable, at least in principle. If the universe came from a quantum fluctuation, it should have certain properties, certain patterns in the cosmic microwave, background, certain structures. We can look for these signatures and see if they're there. So far, we haven't found definitive evidence either way. The search continues. But quantum mechanics offers another even stranger possibility for cosmic origins, one that makes the simulation hypothesis look tame by comparison. Chapter 6. The Multiverse. Are we just one of infinite universes? Okay, buckle up, because we're about to enter territory that sounds like science fiction, but is seriously discussed by top physicists. We're talking about the multiverse. The basic idea of the multiverse is this. Our universe, the one we can observe, is not the only universe. There are others, maybe billions of them, maybe infinite, each one potentially with different laws of physics, different constants, different properties. And here's the kicker. This isn't just wild speculation. The multiverse idea emerges naturally from several different areas of physics. Let me break down the main types. First, there's the quantum multiverse, which comes from the many worlds interpretation of quantum mechanics. You've probably heard of Schrödinger's cat, the thought experiment, where a cat is both alive and dead until you observe it. The standard interpretation says the cat is in a superposition of states until measurement collapses the wave function. But the many worlds interpretation says something different. The wave function never collapses. Instead, every time a quantum measurement occurs, the universe splits. In one universe, the cat is alive. In another, it's dead. Both outcomes happen just in different branches of reality. If this is true, and some very smart physicists think it is, then the universe is constantly branching, creating new parallel universes with every quantum event. And since quantum events happen trillions upon trillions of times per second, the number of parallel universes is growing at an incomprehensible rate. In this view, there are versions of you in other universes making different choices. Universes where you went to a different college, took a different job, never clicked on this video. Every possible quantum outcome is realized somewhere in the multiverse. This sounds crazy, but here's why physicists take it seriously. The mathematics of quantum mechanics naturally describes these branches. You have to add extra assumptions to make the wave function collapse and prevent the universe from splitting. The many worlds interpretation is actually the most straightforward reading of the math. But here's the problem. If you can't travel between these branches, if you can't observe them or interact with them, is the multiverse really science? Or is it metaphysics dressed up in equations? Critics argue that an untestable theory isn't science at all. Supporters counter that the many worlds interpretation makes predictions about quantum interference patterns and decoherence that can be tested. The debate continues. Now, there's a second type of multiverse that comes from cosmic inflation. Remember inflation, that rapid expansion in the early universe I mentioned earlier? Well, according to some versions of inflation theory, called eternal inflation, the inflation process never completely stops. Sure, inflation stopped in our patch of space, creating what we call our universe, but in other regions, inflation is still going on. And in some of those regions, inflation will eventually stop, creating other bubble universes. Each bubble is its own universe, with its own Big Bang, expanding into a larger inflating space. This creates a multiverse of bubble universes, each potentially with different properties. Maybe in some bubbles, the electron has a different mass. Maybe the speed of light is different. Maybe the fundamental constants that govern physics are different. And here's where things get really interesting from a philosophical standpoint. In our universe, the constants of nature seem fine-tuned for life. Change the strength of gravity by a tiny amount, and stars can't form. Change the mass of the electron, and atoms become unstable. Change the strong nuclear force, and elements heavier than hydrogen can't exist. This fine-tuning is extremely precise. We're talking about parameters that need to be set to specific values to within 1 part in a billion or more for a life-permitting universe to exist. Theists have long argued that this fine-tuning points to a designer. The universe looks designed for life, therefore it was designed. But the multiverse offers a different explanation. If there are billions or trillions of universes, each with randomly different constants, then purely by chance, some of them will have the right values to permit life. We find ourselves in one of those universes not because it was designed that way, but because we couldn't exist in any other type of universe. It's called the anthropic principle. We observe a life-permitting universe because a life-permitting universe is the only type we could observe. It's a selection effect. This is deeply unsatisfying to some people because it seems to give up on finding a deeper explanation. Instead of asking, why is the electron mass what it is? We're just saying, it's that way in our universe by chance, and it's different in other universes. We've traded a question about fundamental physics for a story about cosmic lottery tickets. But other physicists find the multiverse compelling precisely because it explains fine-tuning without needing to invoke design or intelligence. It's naturalistic. It doesn't require anything beyond the laws of physics we already know. There's a third type of multiverse proposed by string theory. According to string theory, the fundamental constituents of reality aren't particles, but tiny vibrating strings. Different vibration modes produce different particles, but string theory requires extra dimensions beyond the 3 spatial dimensions. We experience maybe 6 or 7 extra dimensions curled up at incredibly small scales. Here's the thing. There are an enormous number of ways these extra dimensions can be curled up. Some calculations suggest there might be 10 to the power of 500 different possible configurations. That's a 1 followed by 500 zeros. Each configuration would give rise to a universe with different physical properties. This is called the string theory landscape, and it naturally suggests a multiverse where all these different configurations are realized somewhere. Our universe is just one point in this vast landscape of possibilities. Again, this explains fine-tuning through selection rather than through fundamental principles. We're in this particular configuration because it's one of the rare ones that permits observers to exist. Now, here's the million-dollar question. Is any of this testable? For the quantum multiverse, maybe. Some physicists have proposed experiments that might distinguish between the many worlds interpretation and other interpretations of quantum mechanics, though they are incredibly difficult to perform. For the inflationary multiverse, it's harder. Some cosmologists think we might find evidence in the cosmic microwave background, patterns or anomalies that could indicate our universe collided with another bubble universe. Others think we might detect gravitational waves from the era of inflation that could tell us about the multiverse. But these are long shots. For the string landscape multiverse, we're pretty much out of luck. The extra dimensions are too small to observe directly, and there's no way to visit other universes in the landscape to check if they exist. This has led to fierce debates in the physics community. Some scientists argue that the multiverse has become unfalsifiable metaphysics, not real science. Others argue that the multiverse emerges naturally from our best theories, and just because it's hard to test doesn't mean it's not real. Nobel Prize winner David Gross has called the multiverse giving up on the goal of finding fundamental explanations. Lee Smolin has written entire books criticizing the multiverse concept, but others like Max Tegmark and Brian Greene defend it as a natural consequence of physics. Who's right? Honestly, we don't know yet. The multiverse might be real, or it might be a detour in the history of physics that we'll eventually abandon when we find better theories. But here's what's fascinating. The multiverse idea shows how far modern physics has ventured into territory that was once the exclusive domain of philosophy and theology. Questions about reality, existence, and origins that were debated by philosophers for millennia are now being tackled with equations and observations. Speaking of philosophy and theology, we've been dancing around the elephant in the room this whole time. It's time to address it directly. Chapter 7: The Simulation Hypothesis. Are we living in a computer? Program? All right, we need to talk about the simulation hypothesis and I promise you, this is going to mess with your head more than anything we've discussed so far. The basic idea is simple to state, but profound in its implications. What if our entire universe, everything we see and experience, is actually a computer simulation running on some advanced civilization's hardware? This isn't a new idea. Philosophers have pondered whether reality might be an illusion for thousands of years. Descartes wondered if an evil demon might be deceiving him about the nature of reality. Eastern philosophies have long described the physical world as Maya, illusion. The brain in a vat thought experiment asks how you would know if you're not just a brain being fed false sensory inputs. But the modern simulation hypothesis is different. It's not just asking whether we might be deceived about reality. It's proposing a specific mechanism: advanced computer simulation. The person most associated with this idea is philosopher Nick Bostrom, who laid out a famous argument in 2003. His reasoning goes like this. Premise 1. If a civilization reaches a level of technology where they can create realistic simulations of conscious beings, they probably will. Why? Maybe for entertainment, maybe for research, maybe just because they can. Think about how many video games we create. Now imagine video games so advanced that the characters inside are actually conscious and don't know they're in a game. Premise 2. If a civilization creates such simulations, they'll probably create many of them. Not just one, but thousands or millions. After all, once you have the technology, the marginal cost of running another simulation is relatively small. Premise 3. If simulations are possible and likely to be created in large numbers, then there are way more simulated consciousnesses than biological ones. For every real civilization running simulations, there could be millions of simulated civilizations inside their computers. Conclusion? If the above is true, then the vast majority of conscious beings that exist are simulated, not biological. And therefore, statistically speaking, you are probably simulated. Let that sink in for a moment. Bostrom isn't saying we're definitely in a simulation. He's saying that at least one of three things must be true. Either civilizations always destroy themselves before reaching the technology to create realistic simulations, or civilizations that reach that level choose not to create such simulations, or we are almost certainly in a simulation. Those are the only options. Pick your poison. This argument has been taken very seriously by a lot of very smart people. Elon Musk has said he thinks the odds we're in base reality are 1 in billions. Some physicists and computer scientists are actively looking for evidence that we're in a simulation. What kind of evidence? Well, if we're in a simulation, there might be limits to the computational resources available. Just like a video game has a maximum render distance beyond which things get fuzzy, maybe our universe has limits. Some researchers have looked for patterns in cosmic rays or the structure of space-time that might indicate discrete computational steps rather than continuous reality. Others have pointed to quantum mechanics as potential evidence. The fact that particles exist in superposition until observed, that the universe seems to only compute precise values when someone is looking, sounds a lot like how a computer program might work. Why bother rendering something in detail if nobody's looking at it? Save those processor cycles. The speed of light could be the universe's processor speed limit. Planck length, the smallest possible unit of space, could be the pixel size of reality. The uncertainty principle could be a feature, not a bug, limiting how much information needs to be processed at any given moment. Even glitches in the simulation have been proposed. Some people point to phenomena like the Mandela effect, where large groups of people remember events differently than they occurred, as evidence of reality being edited or reloaded from a save point. Now, before you go down the rabbit hole too deep, let's talk about the problems with the simulation hypothesis. First, it suffers from an infinite regress problem. If we're in a simulation, who's to say the simulators aren't also in a simulation? And whoever is simulating them could also be simulated. Turtles all the way down. This doesn't disprove the hypothesis, but it does make you wonder if we've really explained anything or just pushed the question of ultimate reality back a level. Second, the simulation hypothesis makes very few testable predictions. Sure, you can look for glitches or computational limits, but if we don't find them, that doesn't disprove the simulation. Maybe the simulation is just really good. Maybe the simulators patch bugs as they arise. The hypothesis becomes unfalsifiable. Third, there's a philosophical issue called the problem of consciousness. Even if you could simulate a brain neuron by neuron, would the simulation actually be conscious? Or would it just be a very sophisticated imitation of consciousness? We don't even understand how consciousness arises from physical processes, so how can we be sure it could arise from computational processes? Some philosophers argue that consciousness requires more than just information processing. Maybe it requires specific physical substrates. Maybe it requires quantum effects that can't be simulated on a classical computer. If that's true, then even if we're in a simulation, we must be experiencing some form of real, non-simulated consciousness, which undercuts the whole premise. Fourth, and this is more of a practical objection, the simulation hypothesis doesn't actually help us understand our universe any better. It doesn't make new predictions we can test. It doesn't help us build better technologies or cure diseases. It's philosophically interesting, but scientifically sterile. That said, the simulation hypothesis has cultural staying power because it resonates with our increasingly digital existence. We spend hours in virtual worlds, in video games, in social media spaces that are increasingly sophisticated simulations of reality. The line between real and virtual is blurring. A generation that's grown up with virtual reality and AI doesn't find the idea of simulated existence as far-fetched as previous generations might have. And here's something to think about. If we're not in a simulation now, we probably will be eventually. As our technology advances, we're creating increasingly realistic virtual worlds. At some point, maybe in 100 years, maybe in 1,000, we'll likely reach the point where we can create simulations indistinguishable from reality. When that happens, Bostrom's argument kicks in. Once we start creating such simulations, and creating lots of them, the statistical likelihood that we ourselves are simulated goes way up. It's almost like a cosmic inevitability. The moment any civilization gets good enough at simulation, the universe fills up with way more simulated beings than real ones. Unless something stops us from reaching that point. Maybe there's a great filter ahead, some challenge that no civilization survives past. Maybe we'll destroy ourselves before we can create ancestor simulations. Or maybe there's some fundamental law of physics or consciousness that makes such simulations impossible. But if none of those are true, if simulations are possible and we eventually create them, then the odds that you, right now, watching this video, are in base reality drop significantly. How does that make you feel? Okay, we've covered quantum creation, the multiverse, and the simulation hypothesis. But there's one more possibility we need to discuss, and it's the oldest explanation of all. Part 3. The God Question and Philosophical Perspectives. Chapter 8. The Divine Explanation. Could God have created the universe? We've danced around this long enough. Let's talk about God. Now, before half of you click away and the other half get angry, hear me out. Whether you're religious, atheist, or somewhere in between, you have to admit that God created the universe is probably the oldest and still most common answer to the question of cosmic origins. For billions of people around the world, this isn't even a question. Of course, God created the universe. It says so in their holy books. Case closed. But we're going to dig deeper than that because there are actually sophisticated philosophical and scientific arguments for divine creation that go way beyond the Bible says so. Let's start with the Kalam cosmological argument, which has been around since medieval Islamic philosophy, but has been championed in modern times by philosopher William Lane Craig. The argument goes like this. Everything that begins to exist has a cause. The universe began to exist. Therefore, the universe has a cause, and that cause, whatever it is, we might reasonably call God. Now, the first premise seems pretty uncontroversial. In our everyday experience, things don't just pop into existence uncaused. Chairs, cars, planets, stars, they all have causes. The quantum mechanics objection we discussed earlier, where virtual particles pop into existence, is debatable because those particles come from the quantum vacuum, which itself has properties and structure. They're not coming from absolute nothing. The second premise is supported by the Big Bang theory. The universe hasn't existed forever. It had a beginning 13.8 billion years ago. Modern cosmology seems to confirm this. If you accept both premises, the conclusion follows logically. The universe has a cause. But here's where it gets interesting. What kind of cause could create the entire universe? It would have to be outside of space and time, because space and time are part of the universe. It would have to be incredibly powerful to create all of matter and energy. It would have to be non-physical, because the physical universe is what's being created. Those properties, timeless, spaceless, immaterial, enormously powerful, start to sound a lot like traditional descriptions of God. Now, atheist philosophers have objections, of course. Some argue that the first premise is undermined by quantum mechanics. Others argue that the universe might not have actually begun to exist, citing cyclical or eternal models. Still others argue that even if the universe has a cause, why call it God? Why not just call it the cause and leave it at that? But there's a second argument that's even more powerful, the fine-tuning argument. We touched on this earlier when discussing the multiverse, but let's look at it more carefully. The universe appears exquisitely fine-tuned for life. The strength of gravity, the mass of the electron, the strength of the strong nuclear force, the cosmological constant. Dozens of parameters need to have very specific values, often to absurd precision, for a life-permitting universe to exist. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. Slightly weaker, and stars wouldn't form at all. If the strong nuclear force were just 2% stronger, no hydrogen would exist. 2% weaker, and elements heavier than hydrogen couldn't form. Change the ratio of electron mass to proton mass by a tiny fraction, and chemistry as we know it becomes impossible. The odds of all these parameters landing in the life-permitting range by chance are astronomically small. We're talking about odds like 1 in 10 to the power of 120 for the cosmological constant alone. That's a 1 followed by 120 zeros. To put that in perspective, the number of atoms in the observable universe is only about 10 to the power of 80. The level of fine-tuning we're talking about is like throwing a dart at the universe and hitting one specific atom. How do you explain this? There are 3 main options. Option 1, pure chance. We got incredibly, absurdly lucky. The universe just happened to have the right parameters. This is possible, but the odds are so small that it seems deeply unsatisfying. Option 2, the multiverse. There are countless universes with different parameters, and we're in one of the rare ones that permits life. We discussed this earlier. It's a naturalistic explanation that doesn't require God, but it does require believing in an enormous number of universes we can never observe or verify. Option 3, design. The universe was deliberately set up with these parameters by an intelligent designer who wanted life to exist. This is the theistic explanation. Now, which of these explanations is more reasonable is hotly debated. Atheist scientists generally prefer the multiverse explanation, even though it requires believing in an infinite number of unobservable universes. Theists argue that postulating one God is simpler and more elegant than postulating infinite universes. This gets into Occam's razor territory. Which is the simpler explanation? One God or infinite universes? Theists say God is simpler. Atheists say the multiverse is simpler because it doesn't require a conscious, intelligent being with intentions and desires, which are complex properties. There's no clear winner in this debate, which is why it continues. But there's a third argument for God that's less commonly discussed, but philosophically fascinating. The argument from consciousness. We are conscious. We have subjective experiences. There's something it's like to be you, to see red, to feel pain, to experience joy. Philosophers call this qualia, the subjective, qualitative aspects of experience. Here's the puzzle. How does consciousness arise from physical matter? How do neurons firing in your brain, which are just physical and chemical processes, give rise to the felt experience of consciousness? This is called the hard problem of consciousness, coined by philosopher David Chalmers. You can explain, in principle, all the functions of the brain. You can explain how visual processing works, how memory works, how decision-making works. But explaining the function doesn't explain the experience. Why is there something it's like to see red? Why doesn't all this processing happen in the dark, so to speak, without any subjective experience? Materialist philosophers try to solve this by arguing that consciousness is just what brain activity feels like from the inside. But that seems to just restate the problem rather than solve it. Others argue that consciousness is an illusion, but that makes no sense because the existence of the illusion is itself a conscious experience. Some theistic philosophers argue that consciousness points to a non-material aspect of reality, and that this in turn points to God. If consciousness can't be reduced to physical processes, if it's fundamentally non-physical, then materialism is false. And if materialism is false, the door is open to other non-physical realities, like God. This argument is more controversial because consciousness might yet be explained in physical terms. Maybe we just don't understand the brain well enough yet. But the fact that we've made enormous progress in neuroscience without getting any closer to solving the hard problem makes some people think that purely physical explanations might never work. Now, let's address the objections to the God hypothesis, because there are many. First, the who created God objection. If everything needs a cause, what caused God? Theists typically respond that God is uncaused, that God exists necessarily rather than contingently. God doesn't need a cause because God never began to exist. But atheists argue this is special pleading. If you're willing to say God doesn't need a cause, why not just say the universe doesn't need a cause and skip the middle step? Second, the problem of evil. If God created the universe and God is all-powerful and all-good, why is there so much suffering? Why are there natural disasters, diseases, predators eating prey alive? The universe doesn't look designed by a benevolent being. This is probably the strongest argument against theism, and it's one that theologians have struggled with for millennia. Theodicies, explanations for evil, abound. Free will defense, soul-making theodicy, the idea that we can't understand God's purposes. But many people find these unsatisfying. The sheer scale of suffering in the universe seems incompatible with an all-loving creator. Third, the problem of divine hiddenness. If God exists and wants us to know about him, why is the evidence so ambiguous? Why are there sincere seekers who find no trace of God? Why does God's existence seem like a matter of debate rather than obvious fact? Theists respond that God has reasons for not making his existence undeniable, that faith requires some degree of uncertainty, that the evidence is actually quite strong if you're willing to see it. But atheists find this unconvincing. An all-powerful being could make his existence clear without violating free will, so why doesn't he? Fourth, the multiplicity of religions. If God created the universe, which God are we talking about? The Christian God? Allah? Brahman? Zeus? There are thousands of gods that humans have believed in. The fact that religious beliefs correlate so strongly with geography and culture suggests they're human constructs rather than responses to a real deity. Theists respond with various exclusivist, inclusivist, or pluralist positions. Maybe only one religion is true. Maybe multiple religions are responding to the same God in different ways. Maybe religious diversity is part of God's plan. But the fact that intelligent, sincere people reach completely different conclusions about God's nature is at least somewhat problematic for the idea that God's existence and character are obvious. Despite all these objections, the God hypothesis remains popular, and not just among the scientifically illiterate. There are plenty of accomplished scientists who believe in God. Francis Collins, who led the Human Genome Project, is an evangelical Christian. John Polkinghorne was both a particle physicist and an Anglican priest. Freeman Dyson, though not conventionally religious, saw evidence of mind in the cosmos. These aren't people who reject science. They're people who see science as compatible with, or even pointing toward, theism. The key question is this: does science make God unnecessary? Has the naturalistic explanation won? Many atheist scientists think so. They argue that we've explained so much through natural causes, lightning, disease, the diversity of life, the formation of stars and planets, that we should expect natural explanations for everything, including the origin of the universe. God is an increasingly unnecessary hypothesis, but theistic scientists argue the opposite. They say that the more we learn about the universe, the fine-tuning, the mathematical elegance of natural laws, the existence of consciousness, the more it points to design rather than accident. Far from making God unnecessary, modern science reveals a universe that looks designed. Who's right? That's a question that goes beyond what science alone can answer. It enters the realm of philosophy, metaphysics, and personal conviction. What we can say is this: the God hypothesis is an explanation for cosmic origins that can't be easily dismissed. It has problems, sure, but so does every other explanation we've discussed. The Big Bang has problems. Cyclical models have problems. Quantum creation has problems. The multiverse has problems. The simulation hypothesis has problems. Maybe the truth is that the question of ultimate origins is simply beyond our capacity to answer with certainty. Maybe we're like ants trying to understand quantum mechanics. The question is too big, too fundamental for our limited cognitive abilities. Or maybe we're on the verge of a breakthrough. Maybe the next generation of particle accelerators, space telescopes, or theoretical breakthroughs will finally give us the answer. Let's explore what the cutting edge of modern science is telling us. Chapter 9: What Modern Physics Really Says. All right, it's time to bring this all together and talk about where we actually stand. What does modern physics, with all its tools and observations and theories, really tell us about the origin of the universe? The honest answer? We don't know. But we know more than we've ever known, and the picture that's emerging is weirder than almost anyone expected. Let's start with what we're pretty confident about. The universe is expanding. This is observed fact, confirmed by countless measurements. Running the expansion backward leads to a hot, dense, early state. This is also well supported by evidence: the cosmic microwave background, the abundance of light elements, the distribution of galaxies. So the Big Bang, understood as the event where the universe transitioned from a hot, dense state to an expanding, cooling one, almost certainly happened. That's not really in dispute anymore among serious physicists. But, and this is crucial, the Big Bang doesn't tell us about the absolute origin. It tells us about the earliest state we can reliably describe with current physics. It's like having a video that starts playing 1 second into an event. You can see what happened from 1 second onward, but you don't know how the event started or what was there before. This is where all the uncertainty lies. What came before the Big Bang? What caused it? What was the initial state? These are the questions where physics is still groping in the dark. Modern theories are trying to push further back. Inflation theory tries to describe what happened in the first tiny fraction of a second. Loop quantum gravity and string theory try to describe what happens at the Planck scale, where both quantum mechanics and gravity are important. These theories make different predictions about the very beginning, but here's the problem. We can't test most of these predictions. The energies involved in the earliest moments of the universe are so high that we can't recreate them in particle accelerators. The Large Hadron Collider is the most powerful machine ever built, and it can't get anywhere close to the energies that existed a trillionth of a second after the Big Bang. So we're stuck making theoretical models and hoping we can find indirect evidence in observations of the cosmic microwave background, or in the distribution of galaxies, or in gravitational waves. We're looking for fingerprints of the earliest moments left imprinted on the universe we see today. And we have found some intriguing hints. The patterns in the cosmic microwave background match predictions from inflation theory surprisingly well. Observations of gravitational waves have opened a new window into the early universe. Measurements of the universe's geometry have confirmed predictions about flatness. But we've also found anomalies and tensions. The Hubble tension I mentioned earlier is still unresolved. There are some patterns in the cosmic microwave background that don't quite match the standard model. Dark matter and dark energy remain complete mysteries despite decades of searching. What does cutting-edge theoretical physics say about origins? String theory, if it's correct, suggests the universe has extra dimensions, and that our Big Bang might have been a collision of higher dimensional brains. Loop quantum gravity suggests that the Big Bang wasn't a singularity, but a big bounce from a previous contracting phase. Quantum cosmology suggests the universe might have tunneled into existence from nothing via quantum mechanics. Each of these theories is mathematically sophisticated and potentially revolutionary. Each makes some predictions that could, in principle, be tested, but none has been definitively confirmed yet. We're in a period of theoretical abundance but empirical scarcity. Here's something that might surprise you. Many physicists are coming around to the idea that the question, what created the universe, might not have a single definitive answer. Or rather, the answer might depend on which framework you're using to ask the question. In the framework of general relativity, the universe began with the Big Bang. In the framework of quantum mechanics, maybe it quantum tunneled from a vacuum state. In the framework of eternal inflation, our universe is one bubble in an eternally inflating multiverse. In a theological framework, God created it. Are these competing explanations, or are they describing the same reality from different perspectives? Some philosophers argue that asking which framework gives the real answer is like asking whether it's really 3 p.m. or really 1500. Both describe the same moment. They're just using different conventions. This idea that reality might be framework dependent is controversial and unsettling. We want there to be one true story of how the universe began. But maybe the universe is too complex, too strange, for any single narrative to capture completely. What does this mean for our original question? Is the Big Bang really what created the universe? The answer seems to be yes and no. Yes, the Big Bang describes the earliest phase of cosmic evolution that we can reliably study. No, it probably doesn't describe the absolute origin of existence itself. The Big Bang is a beginning, but maybe not the beginning. And this brings us to perhaps the most profound realization: the limits of science. Chapter 10: The Limits of Science and the Edge of Knowledge. Here's something that might shock you. Science might never be able to answer the question of what created the universe. Not because scientists aren't smart enough, or because we don't have good enough equipment, but because the question might be fundamentally beyond the scope of scientific inquiry. Let me explain what I mean, and this is important. Science works by making observations, forming hypotheses, testing predictions, and refining theories. It's incredibly powerful within its domain. We've used science to understand atoms, genes, stars, galaxies. We've cured diseases, split atoms, and sent robots to Mars. Science works. But science has inherent limitations. It can only study things that are observable, that interact with the physical world in measurable ways. It requires repeatability and testability. If you can't observe something, measure it, or test predictions about it, science can't really get a grip on it. Now, think about the origin of the universe. By definition, we're talking about something that happened once that we can't repeat, that we can't directly observe because we're looking at it from billions of years in the future. We can see the aftermath, sure, but we can't rewind and watch it happen. Moreover, if we're asking about the absolute origin, about why there's something rather than nothing, we're asking a question that might be outside the causal chain that science studies. Science is great at explaining how one thing causes another thing within the universe. But can it explain why the universe itself exists? That's a different kind of question. This is what philosophers call a category error. It's like asking what color mathematics is or what temperature justice has. The question doesn't compute because you're applying concepts from one domain to another where they don't fit. Some scientists and philosophers argue that asking what caused the universe is like asking, what's north of the North Pole? The question seems meaningful, but it's actually nonsensical. If time itself began with the Big Bang, there is no before to ask about. The concept of causation, which requires time, doesn't apply. But here's where it gets philosophically deep. Even if science can't answer the ultimate question, does that mean there is no answer? Or does it just mean science isn't the right tool for this particular job? This is where we venture into metaphysics, the branch of philosophy that deals with the fundamental nature of reality. Metaphysics asks questions that science can't. Why does anything exist? Why are the laws of physics the way they are? What is the nature of causation itself? Science assumes certain things to get started. It assumes the universe is rational and comprehensible. It assumes the laws of nature are consistent. It assumes our observations are reliable. But why are these assumptions justified? Science can't answer that question without circular reasoning. You can't use science to prove that science works. That's begging the question. Some scientists are comfortable saying that these are just brute facts. The universe is comprehensible because it is. The laws of nature are consistent because they are. Deal with it. This is sometimes called the shut up and calculate approach, famously associated with quantum mechanics, but applicable more broadly. Other scientists and philosophers find this unsatisfying. They want deeper explanations. Why is the universe comprehensible? Maybe because it was designed by an intelligence to be comprehensible. Maybe because we're part of the universe, so we've evolved to comprehend it. Maybe because only comprehensible universes can give rise to observers to comprehend them. These questions don't have scientific answers, but they're not meaningless. They're asking about the foundations that make science possible in the first place. Here's another profound limitation: the problem of induction. Science relies on the assumption that the future will resemble the past, that patterns we've observed will continue. But this assumption can't be proven scientifically. Any attempt to prove it would require assuming it, which is circular. The philosopher David Hume pointed this out centuries ago, and it's still a philosophical puzzle. We use science because it works, because it's given us incredible predictive power and technological advancement. But we can't prove that it will continue to work tomorrow. We assume it as an article of faith. This doesn't mean science is unreliable. It means science rests on certain unprovable assumptions. And when we're asking questions about the origin of everything, about why the universe exists at all, we might be pushing beyond where those assumptions apply. Now, some scientists get frustrated with this kind of philosophical talk. They say philosophy is just word games, that what matters is empirical results. If your theory makes testable predictions that turn out to be correct, it's a good theory. End of story. But that attitude misses something important. Science can tell us how the universe works. It can't tell us why the universe exists, or whether existence has meaning or purpose, or what we should value. These are philosophical questions, and they matter. The origin of the universe is right at the boundary between science and philosophy. It's a question that science can partially address, but probably can never fully answer. And that's okay. It doesn't diminish science. It just reminds us that there are different kinds of questions and different tools for addressing them. So where does this leave us? We've looked at the Big Bang Theory, cyclical models, quantum creation, the multiverse, the simulation hypothesis, and the God hypothesis. We've explored the cutting edge of physics and the limits of scientific knowledge. What conclusion can we draw? Chapter 11. Integration. Weighing the evidence. Let's take stock of where we are. We've covered a lot of ground, and your head is probably spinning. Mine is too, honestly, and I research this stuff. So let's try to bring some clarity to the chaos. First, let's acknowledge what we know with high confidence. The universe is expanding. It was once much hotter and denser. The Big Bang, understood as the transition from that hot, dense state to the expanding universe we see today, almost certainly happened about 13.8 billion years ago. The evidence for this is overwhelming. Multiple independent lines of observation all point to the same conclusion. This isn't speculation. This is about as well established as anything in cosmology gets. But the Big Bang Theory, as we've discussed at length, doesn't explain the absolute origin. It describes what happened after some initial state, but it doesn't tell us what that initial state was or where it came from. When we try to push further back to understand the true beginning, we enter much more speculative territory. Let's evaluate the main contenders. Cyclical universe models are elegant and avoid the problem of an absolute beginning. They've been around for millennia in various forms, and modern physics has given them new mathematical rigor. But they face serious challenges with entropy, and with observations showing the universe's expansion is accelerating, not slowing down as you'd need for eventual collapse and rebirth. Could these challenges be overcome? Maybe. Perhaps there are mechanisms for resetting entropy we don't understand. Perhaps dark energy's properties will change in the future. But right now, these are speculative fixes to make the model work. Quantum creation, the universe from nothing, is intriguing because it uses known physics, quantum mechanics, to explain origins. The idea that the universe could be a quantum fluctuation is mathematically plausible, but it requires pre-existing quantum laws, which means you haven't really explained where everything came from. You've just shifted the question to where the laws came from. Also, the jump from microscopic quantum fluctuations to an entire universe is enormous and not well explained. The math works in some models, but it feels like we're missing something. Why would a quantum fluctuation persist as a universe for billions of years rather than disappearing instantly like virtual particles do? The multiverse is probably the most popular explanation among physicists right now, at least among those working in inflation theory and string theory. It explains fine-tuning naturalistically, and it emerges naturally from some of our best theories. But it has a huge problem: testability. If other universes are fundamentally unobservable, can we really call it science? We're postulating an infinite number of unobservable entities to explain observations in our one universe. That's a heavy ontological burden. Some physicists are okay with this. They argue that the multiverse emerges from theories we're testing in other ways, so it's not ad hoc. Others think the multiverse represents a crisis in physics, a descent into unfalsifiable speculation. The jury is still out. Maybe we'll find indirect evidence. Maybe the whole idea will be abandoned when better theories come along. Time will tell. The simulation hypothesis is fascinating from a philosophical standpoint, but it doesn't really solve the origin problem. Even if we're in a simulation, someone or something created the simulation. You've just moved the question up one level. Plus, the hypothesis makes few testable predictions and doesn't help us understand our universe better. It's more of a thought experiment than a serious scientific theory, though it does raise interesting questions about the nature of reality and consciousness. And then there's God. The theistic explanation has the advantage of being simple in one sense. One intelligent, powerful being created everything. It explains fine-tuning. It explains why the universe is comprehensible. It explains the existence of consciousness. But it has disadvantages too. It doesn't make specific, testable predictions. It doesn't explain God's own existence. It faces the problem of evil and the problem of divine hiddenness. And it requires accepting the existence of a non-physical, supernatural entity, which is a big metaphysical commitment. Whether you find the God hypothesis plausible depends a lot on your prior philosophical commitments. If you're a philosophical naturalist who thinks everything can be explained by natural causes, you'll reject God and prefer the multiverse or quantum creation despite their problems. If you're open to supernatural explanations, you'll find the design argument compelling. This is why the debate continues. It's not just about evidence. It's about how you interpret the evidence through your philosophical lens. So which explanation is correct? Here's my honest assessment. We don't know, and we might never know with certainty. Each explanation has strengths and weaknesses. Each fits some data better than others. None is without serious problems. The question of ultimate origins might simply be beyond our current capacity to answer definitively. But that doesn't mean all explanations are equally good. We can evaluate them based on criteria like explanatory power, simplicity, testability, and consistency with observations. When we do that, some patterns emerge. The standard Big Bang model explains a lot and is well tested, but it doesn't explain origins. Models that try to explain origins, whether scientific or theological, all require accepting some unprovable assumptions. Cyclical models assume cycles can overcome entropy. Quantum creation assumes quantum laws are fundamental and unexplained. Multiverse models assume unobservable universes. God hypotheses assume an unexplained supernatural being. You can't escape assumptions. The question is which assumptions you find most reasonable. For what it's worth, here's where I land, and you're free to disagree. I think the question of absolute origins might be fundamentally unanswerable by science alone. Science can trace the history of the universe back to incredibly early times, and it's made amazing progress. But asking why there's something rather than nothing, why the laws of physics exist, why the universe is comprehensible, these are philosophical questions that require philosophical frameworks to address. That doesn't mean they're meaningless. It means they're different kinds of questions. My suspicion, and this is just informed speculation, is that the true explanation for cosmic origins involves both scientific and philosophical components. Understanding the mechanism of creation, whether it's quantum tunneling or brain collisions or something else, is a scientific question. Understanding why that mechanism exists, why it produces universes, why anything exists at all. Those are philosophical questions. We need both science and philosophy working together to make progress on this deepest of mysteries. But let me be clear, I could be completely wrong. Maybe there is a pure scientific explanation that will emerge when we finally develop a theory of quantum gravity. Maybe there's a pure philosophical or theological answer that will become evident when we think more clearly about the nature of being and causation. The honest position is epistemic humility. We don't know. But we can keep searching, keep questioning, keep refining our theories and observations. That's what makes this exciting. Now, let's talk about what the future might hold. Chapter 12. The future of cosmology. What comes next? So where do we go from here? What are the next steps in understanding cosmic origins? What breakthroughs might we see in the next few decades? The good news is that we're entering a golden age of observational cosmology. New telescopes, new experiments, new technologies are coming online that will let us probe the early universe with unprecedented precision. The James Webb Space Telescope is already transforming our view of the early universe. It's observing galaxies that formed just a few 100 million years after the Big Bang, testing our theories of structure formation. It's measuring the properties of the first stars and finding surprises that don't quite fit standard models. These observations will help us refine our understanding of cosmic history and might reveal hints about what came before the Big Bang. Upcoming gravitational wave detectors, like LISA, will observe ripples in space-time from the earliest moments of the universe. Gravitational waves from cosmic inflation, if they exist, and if we can detect them, would be smoking gun evidence for inflation theory. They'd tell us about physics at energy scales we can never reach with particle accelerators. Next-generation particle accelerators, if they get built, might discover new particles or forces that point toward theories of quantum gravity. String theory and loop quantum gravity make different predictions about what we should find at high energies. Data from these machines could help us choose between competing theories. There are also experiments trying to detect dark matter directly. If we can figure out what dark matter actually is, it would be a huge step forward. Right now, dark matter is a placeholder, a name for something we don't understand. Identifying it would constrain models of the early universe significantly. And there are experiments looking for proton decay, testing whether matter itself is stable or gradually deteriorating. Some grand unified theories predict protons should very rarely decay. Finding this would revolutionize physics and cosmology. On the theoretical front, there's been exciting progress in quantum gravity. Loop quantum cosmology has shown that the Big Bang singularity might be replaced by a bounce in their framework. String theory continues to develop, with new insights into how extra dimensions might behave. There's also interesting work on the emergence of space-time itself. Some physicists are exploring whether space and time are fundamental or whether they emerge from something more basic, like quantum information. If space-time is emergent, the question of cosmic origins looks completely different. Maybe the universe didn't begin in time because time itself emerged later. These are radical ideas, but they're being seriously explored by top physicists. The next few decades might see major paradigm shifts in how we think about reality itself. There's also growing recognition that solving the origin problem might require new mathematical tools. Our current mathematics is incredibly powerful, but maybe it's not suited to describing the earliest moments or the transition from nothing to something. Some physicists are exploring alternative mathematical frameworks, non-commutative geometry, categorical quantum mechanics, things that sound like gibberish to most people, but might be necessary to describe reality accurately. And here's something exciting. Artificial intelligence is starting to play a role in theoretical physics. AI systems can find patterns in data that humans miss, can explore vast solution spaces to theoretical problems, can even propose new models. It's possible that AI will help us crack problems that have stumped human physicists for decades. Of course, there's also the possibility that we'll hit fundamental limits. Maybe there's a limit to how far back we can observe, not just practical, but in principle. Maybe the universe's earliest moments are forever hidden behind a veil we cannot pierce. Some physicists have argued that the Planck time, about 10 to the power of minus 43 seconds, represents a fundamental limit beyond which space-time itself becomes meaningless. If that's true, we can never know what happened before that time. The question becomes physically meaningless, like asking what's south of the South Pole. But even if that's true, we can still make progress. We can develop better theories that work up to that limit. We can test them against observations. We can constrain the possible explanations, even if we can't definitively choose between them. The pursuit of knowledge about origins isn't just about finding the answer. It's about refining our questions, developing better tools, pushing the boundaries of what's knowable. Even if we never get a complete answer, the journey teaches us an enormous amount. And here's something that often gets overlooked. The search for cosmic origins has practical benefits. Technologies developed for particle physics have given us the World Wide Web, medical imaging devices, and new materials. Space telescopes have advanced optics and sensors that end up in consumer products. Pure research into fundamental questions pays dividends in unexpected ways. More importantly, understanding where we came from shapes how we think about our place in the cosmos. Are we a cosmic accident, a quantum fluctuation that happened to persist? Are we part of an eternal cycle of universes? Are we simulated? Are we created with purpose? The answer to that question, or even the pursuit of that answer, influences how we see ourselves and our significance. It's not just abstract philosophy. It affects how we live, what we value, how we treat each other and our planet. If we're just an accident in an indifferent universe, maybe nothing matters. Or maybe it means everything matters precisely because it's all we have. If we're created with purpose, maybe we have obligations to fulfill that purpose. Or maybe we have the freedom to define our own purpose. These are questions that go beyond science, but science informs them. The more we learn about the universe's origins, the more context we have for wrestling with these existential questions. So what does the future hold? My prediction is that we'll continue to make incremental progress. We'll refine the Big Bang model, nail down more parameters, rule out some theories, and give others more credibility. We might detect gravitational waves from inflation. We might identify dark matter. We might develop a working theory of quantum gravity. But I don't think we'll get a simple, definitive answer to the question, what created the universe? Anytime soon. The question is too big, too fundamental. It touches on science, philosophy, theology, mathematics, logic itself. We'll chip away at it. We'll learn more. But complete understanding? That might always be beyond our grasp, and maybe that's okay. Maybe part of being human is living with mystery, with uncertainty, while never stopping the search for truth. Now, let's bring this all home. Chapter 13. The Dark Universe. What we're really made of. Okay, let's talk about something that's going to absolutely blow your mind. Remember how I mentioned that we only understand about 5% of the universe? Let's dive deep into that rabbit hole because what we're about to discover is going to make you question everything you thought you knew about reality. Right now, as you're watching this video, you're surrounded by dark matter. It's passing through your body, through the walls, through the earth itself. Billions of dark matter particles are streaming through you every single second, and you can't feel them, can't see them, can't detect them in any normal way. This isn't science fiction. This is what the math tells us must be true. Think about it this way. When astronomers look at galaxies rotating, they notice something weird. The outer edges of galaxies are spinning way too fast. According to the laws of gravity and the amount of visible matter we can see, those outer stars should be flying off into space like water droplets off a spinning wheel, but they're not. Something is holding them in place. That something is dark matter. There's 5 times more dark matter in the universe than regular matter. 5 times. Everything you can see, every star, every planet, every galaxy, every atom in your body, that's the minority. The vast majority of matter in the universe is something we've never directly detected. And here's where it gets even crazier. Dark energy makes up about 68% of the universe. So dark matter is 27%, normal matter is 5%, and dark energy is 68%. But what is dark energy? Nobody knows. It's the force pushing the universe apart, accelerating its expansion, and we have absolutely no idea what it is. Let me put this in perspective. Imagine you're a detective investigating a crime scene, and you can only see 5% of the evidence. You have to guess what happened based on that tiny fraction. That's where we are with the universe. We're trying to understand cosmic origins when we can't even explain 95% of what the universe is made of. Some scientists think dark matter might be WIMPs, weakly interacting massive particles. Others think it could be axions, or sterile neutrinos, or primordial black holes left over from the Big Bang. We've built incredibly sensitive detectors, deep underground, shielded from cosmic rays, trying to catch dark matter particles. So far, nothing definitive. And dark energy? Even more mysterious. Einstein actually predicted something like it with his cosmological constant, but he called it his biggest blunder and took it back. Turns out, he might have been right the first time. But we still don't know if dark energy is a property of space itself, or a new field, or something else entirely. Here's why this matters for our origin question. Whatever dark matter and dark energy are, they were there from the beginning. They played crucial roles in how the universe evolved from the Big Bang to now. Understanding them isn't just about completing our picture of the universe. It's about understanding how the universe could exist at all. If dark energy had been slightly stronger, the universe would have expanded so fast that galaxies could never form. Slightly weaker, and the universe might have collapsed back on itself billions of years ago. The value we observe is in this incredibly narrow range that allows structure and life to exist. Is that fine-tuning, design, multiverse selection, blind luck? We're back to the same questions, but now with even more mystery because we don't even know what we're talking about when we say dark energy. Some cutting-edge theories propose that dark matter and dark energy might be connected, two aspects of some deeper phenomenon we haven't grasped yet. Others suggest they might be evidence of extra dimensions leaking into our reality. Some even propose they're signs we're living in a simulation where the programmers are running out of processing power and have to approximate most of the universe. The point is, we're not just missing a few puzzle pieces. We're missing most of the puzzle, and we're not even sure what the picture is supposed to look like. And this brings up something profound. Maybe the reason we can't definitively answer the origin question is because we're asking it in a language we don't fully understand. It's like trying to write poetry in a language where you only know 5% of the words. You might get the gist across, but the full meaning, the full beauty, the full truth, that's going to elude you. What if dark matter and dark energy are clues? What if they're breadcrumbs left by whatever created the universe, pointing us toward a deeper truth we haven't grasped yet? This is why some physicists are obsessed with finding dark matter particles or understanding dark energy. It's not just about completing the periodic table or adding to textbooks. It's about potentially unlocking the deepest mysteries of existence itself. Let's move on to something even stranger. Chapter 14: Quantum Weirdness and Reality's Fabric. All right, strap in, because we're about to enter the bizarre world of quantum mechanics, and I promise you, this is going to mess with your understanding of reality in ways that might actually be relevant to how the universe began. You've probably heard that quantum mechanics is weird. Particles can be in two places at once, they can be entangled across vast distances. Observation affects reality. But let me tell you exactly how this weirdness might relate to cosmic origins, because this is where things get absolutely wild. First, let's talk about quantum superposition. At the quantum level, particles don't have definite properties until they're measured. An electron doesn't have a specific location until you look at it. It exists in a superposition of all possible locations simultaneously. This isn't a limitation of our knowledge. It's not that the electron is somewhere and we just don't know where. According to quantum mechanics, the electron genuinely doesn't have a specific location until measurement collapses the superposition into a definite state. Now, here's where this gets relevant to origins. Some physicists propose that the entire universe might have started in a quantum superposition, not in one specific state, but in a superposition of all possible states. The measurement that collapsed this cosmic superposition into our specific universe could have been the Big Bang itself. Think about that. The universe didn't start in one definite configuration. It started in all possible configurations at once, and somehow, through quantum processes we don't fully understand, it collapsed into the specific universe we observe. This is related to an idea called the wave function of the universe, proposed by physicists like Stephen Hawking and James Hartle. They tried to write down a quantum mechanical equation describing the entire universe, treating it like one giant quantum system. In their model, the universe doesn't have a beginning in the traditional sense. Instead, time itself emerges from a timeless quantum state. Asking what came before the Big Bang is like asking what's north of the North Pole, not because the question is meaningless, but because the concept of before doesn't apply to a timeless quantum state. Mind-bending, right? But it gets weirder. Quantum entanglement is this phenomenon where two particles can be connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and didn't like it, but experiments have proven it's real. Now, here's the thing. In the earliest moments of the Big Bang, when the entire observable universe was smaller than an atom, everything was entangled with everything else. Every particle that exists now was in intimate quantum contact with every other particle. That entanglement has mostly been lost through a process called decoherence, where quantum systems interact with their environment and lose their quantum properties. But some physicists think remnants of that primordial entanglement might still exist, connecting distant parts of the universe in ways we don't yet understand. Could this explain the horizon problem? Could primordial quantum entanglement be the reason the universe is so uniform, even in regions that should never have been in causal contact? Maybe. The math is complicated, and the jury is still out. But here's something that will really bake your noodle. Some interpretations of quantum mechanics suggest that reality is fundamentally information-based. The universe isn't made of matter and energy at the deepest level. It's made of information, bits and qubits, quantum states encoding data. If that's true, asking what created the universe becomes asking what created the information. Where did the first bit come from? Why does information exist rather than nothing? Some physicists and philosophers have proposed that information might be more fundamental than physical reality. That consciousness and information are the true bedrock of existence. and the physical universe is what emerges when information is organized in certain ways. This sounds mystical, but it's actually grounded in some serious physics. The holographic principle, for example, suggests that all the information in a region of space can be encoded on its boundary, like a hologram. The interior is in some sense redundant, derivable from the surface information. If the universe is fundamentally informational, maybe it was created by something that processes information. Maybe that's consciousness. Maybe that's God. Maybe that's a computer running a simulation. Maybe it's something else we can't even conceive of. Or maybe the universe created itself through a self-referential loop of information processing. This sounds impossible, but in quantum mechanics, you can have closed time-like curves, situations where causation loops back on itself. Maybe the universe is its own cause, a self-creating, self-sustaining loop of quantum information. Your head hurting yet? Good. That means you're paying attention. The point is, quantum mechanics opens up possibilities for cosmic origins that classical physics never could. The weirdness of the quantum world, the superposition, the entanglement, the role of observation and information, all of this might be essential to understanding how something can come from nothing, or how the universe can be its own cause. We're not done with quantum weirdness. Let's talk about something even stranger. Chapter 15, Time's Arrow and the Entropy Enigma. Let me ask you a question that seems simple, but is actually one of the deepest mysteries in physics. Why does time move forward? No, seriously, think about it. Most of the laws of physics work the same, whether time is running forward or backward. If you filmed a collision between two billiard balls and played it in reverse, you wouldn't be able to tell. The laws of motion work both ways. But we all know time has a direction. Eggs break but don't unbreak. People age but don't unage. Coffee cools down but doesn't spontaneously heat up. The universe seems to have an arrow pointing from past to future, but why? The answer, according to physics, is entropy. The second law of thermodynamics says that entropy, disorder, always increases in a closed system. Things go from ordered to disordered, from structured to chaotic, from low entropy to high entropy. And that increase defines time's arrow. But here's the problem, and this is crucial for understanding cosmic origins. The early universe, right after the Big Bang, was in an incredibly low entropy state. It was highly ordered, all that matter and energy concentrated in a tiny space, in a very specific configuration. This shouldn't be possible. If entropy always increases, if the universe is constantly moving from order to disorder, how did it start out in such an ordered state? It's like finding a deck of cards perfectly sorted by suit and rank and being told that it got that way by random shuffling. The odds are essentially zero. This is called the past hypothesis, and it's one of the biggest unsolved problems in physics. We have to assume that the universe started in a very low entropy state, but we have no good explanation for why. Some physicists think this points to something beyond the Big Bang, some mechanism or reason that set the initial conditions. Maybe the universe before our Big Bang was in a high entropy state, and somehow entropy was reset during the bounce or collision that created our universe. But how? We don't know. Others think the low entropy beginning might be related to gravity. Gravity is weird because unlike other forces, gravitational systems have negative heat capacity. When they lose energy, they get hotter, not cooler. Maybe gravity plays a special role in entropy that we don't understand, and maybe that's connected to how the universe began. Here's where it gets even more mind-bending. Some physicists have proposed that time itself might not be fundamental. Just like space might emerge from something more basic, time might emerge from a timeless quantum state. In this view, the Big Bang isn't an event in time. It's the emergence of time itself from a timeless quantum realm. Before the Big Bang, there was no before. Not because time started then, but because the concept of time doesn't apply. This solves the entropy problem in a weird way. If there's no time before the Big Bang, there's no entropy before the Big Bang. The question of why entropy was low becomes meaningless. It's like asking why the temperature was cold before temperature existed. But this raises new questions. How does time emerge? What determines the direction? Why does it emerge at all? Some theories propose that time emerges when quantum systems decohere, when the universe transitions from a quantum superposition to definite classical states. The arrow of time is the direction of increasing decoherence, increasing entanglement with the environment, increasing irreversibility. Others propose that time is an illusion, that the true, fundamental description of reality is timeless. And we experience time as a sequence of correlated states, like frames in a movie. The movie exists all at once, but when you watch it, you experience it frame by frame, creating the illusion of time flowing. This is called the block universe view, and Einstein's relativity actually supports it. In relativity, past, present, and future all exist equally. Time is just another dimension like space. The flow of time, the feeling that the present is somehow special, that might just be how our consciousness navigates through a timeless four-dimensional reality. If that's true, then the Big Bang isn't the beginning of time. It's just one end of the time dimension. Asking what came before is like asking what's west of the westernmost point on Earth. The question assumes a direction that doesn't exist. But does this really solve anything? Or does it just reframe the mystery? If the block universe exists timelessly, why does it exist? What determines its structure? We've gotten rid of temporal creation, but we still have to explain existence itself. The entropy problem connects to origins in another way, too. If the universe is finite in age, and entropy always increases, then eventually the universe will reach maximum entropy, a state called heat death, where no more work can be done, no more structure can form. Everything is in equilibrium. The universe becomes a uniform, boring, dead place. This heat death is trillions upon trillions of years in the future, so don't worry about it keeping you up tonight. But it raises questions. If the universe is headed toward heat death, how did it start so far from heat death? If cyclical models are correct, how does entropy get reset between cycles? Some physicists propose that the universe might not reach heat death, that something might intervene. Maybe dark energy will change behavior. Maybe quantum fluctuations will create new big bangs. Maybe the universe will collapse before heat death. Others accept heat death as inevitable and try to understand what it means. In the very far future, will quantum fluctuations in the nearly dead universe create random Boltzmann brains, conscious observers that pop into existence by pure chance? If so, you're more likely to be a Boltzmann brain than a real evolved being, which is philosophically disturbing. The point is, the arrow of time and the entropy problem are deeply connected to cosmic origins. Understanding why time flows forward requires understanding where the universe came from and why it started in such an improbable, low entropy state. And that's a mystery we're nowhere close to solving. Chapter 16, The Mathematics of Creation. Let's talk about something that doesn't get enough attention: the unreasonable effectiveness of mathematics in describing the universe. And trust me, this is going to lead us somewhere profound about creation. Here's what I mean. Mathematics is a human invention, right? We created numbers, equations, geometry to help us count sheep and measure fields. But somehow, this human-invented language describes the deepest workings of the universe with shocking precision. Einstein's equations predict gravitational waves, and 100 years later, we detect them exactly as predicted. Quantum mechanics makes predictions accurate to 10 decimal places. Mathematical theorems about abstract spaces turn out to describe particle physics. Why? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. Why should our abstract mathematical games have anything to do with physical reality? It's not obvious that they should. Some people say this is evidence of design. The universe runs on mathematics because it was designed by a mathematical mind. God is a mathematician, and creation is his theorem made real. This is actually a very old idea. Plato thought mathematics existed in some perfect realm of forms, and the physical world was just an imperfect reflection of mathematical reality. Others say we've got it backwards. Mathematics doesn't describe reality. Reality is mathematics. The universe doesn't just obey mathematical laws. The universe is a mathematical structure. Physical stuff, matter and energy, that's just what certain mathematical structures look like from the inside. This is the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. In his view, our universe is one mathematical structure among infinite possible mathematical structures. Each structure that's complex enough contains conscious observers, and those observers experience that mathematical structure as physical reality. This might sound crazy, but think about it. What is an electron, really? It's not a little ball. It's a pattern of quantum fields. And what are quantum fields? They're mathematical objects, solutions to equations. At the deepest level, when you strip away all the physical intuitions, what you're left with is pure mathematics. If the universe is mathematics, then asking what created the universe becomes asking what created mathematics. And here's the thing: mathematics isn't created. Mathematical truths exist necessarily. 2 + 2 = 4 in all possible worlds. The Pythagorean theorem is true regardless of whether any physical triangles exist. So if the universe is mathematical, maybe it exists necessarily too. Maybe it couldn't not exist, just like mathematical truths couldn't not be true. The question, why is there something rather than nothing, dissolves because mathematical structures necessarily exist. But this raises new problems. Why this mathematical structure? Why not a different one? There are infinitely many possible mathematical structures. Why do we find ourselves in this particular one? The answer, according to Tegmark, is the multiverse again. All mathematical structures exist, each as a universe. We're in this one because we couldn't exist in simpler ones. It's anthropic selection applied to mathematics. Now, not everyone buys this. Many philosophers and physicists think mathematical structures are abstract objects that don't have causal powers. They can describe reality, but can't create it. A blueprint doesn't build a house. But maybe that distinction between abstract and concrete isn't as clear as we think. What if the distinction is an illusion, an artifact of how our brains categorize things? What if mathematical existence and physical existence are the same thing? Here's another angle. Some of the deepest theories in physics suggest that information is more fundamental than matter, and information is inherently mathematical. A bit is abstract. It's a mathematical concept. If reality is information all the way down, then reality is mathematical all the way down. Quantum mechanics supports this. The state of a quantum system is described by a wave function, which is a mathematical object in an abstract space called Hilbert space. And increasingly, physicists think the wave function is reality, not just a description of reality. The map is the territory. String theory pushes this even further. In string theory, the fundamental objects are vibrating strings in higher dimensional space. But these strings aren't made of anything. They don't have substructure. They are purely mathematical entities, solutions to equations. Yet supposedly, they give rise to all the particles and forces we observe. If strings are real and they're purely mathematical, then mathematics is literally creating physical reality. Or rather, mathematics is physical reality. This has profound implications for origins. If creation is just the instantiation of a mathematical structure, then maybe no creator is needed. The structure exists necessarily, mathematically, and consciousness emerges within it to observe it. But here's a counter-argument. Even if the universe is mathematical, even if it exists necessarily, that doesn't explain why mathematics exists. Why are there mathematical truths? Why is logic logical? Why does anything follow from anything else? These questions seem to point beyond mathematics to something even more fundamental. Maybe consciousness, maybe God, maybe something we can't conceive of. Some philosophers argue that logic and mathematics require a ground, something to make them real rather than just abstract possibilities. That ground, they say, is a necessary being, God, whose nature is logical and mathematical, and who thinks all mathematical truths into existence. Others say that's backwards, that God, if God exists, must be bound by logic and mathematics because they're more fundamental than any being. God can't make contradictions true because contradictions aren't things that can be true. We're deep in philosophical weeds now, but this matters. If mathematics can create itself, if it exists necessarily, and gives rise to physical universes, then we have a naturalistic answer to cosmic origins. If mathematics requires something beyond itself to ground it, we might need God or something like God after all. The honest answer: we don't know. The relationship between mathematics and physical reality is one of the deepest unsolved mysteries in philosophy of science. What we can say is this: the fact that the universe is mathematical is not a trivial fact. It's weird, profound, and might be a clue to understanding creation itself. Chapter 17: Consciousness and the Cosmic Mind. Now we need to talk about the most mysterious thing in the universe: you. Or more precisely, your consciousness, your subjective experience, your awareness. Because consciousness might be the key to understanding cosmic origins. And that's going to sound crazy until I explain it. We've talked about matter, energy, quantum mechanics, mathematics, but none of that explains why there's something it's like to be you. Why you have inner experiences, qualia, a first-person perspective on reality. This is the hard problem of consciousness, and it's remained unsolved despite centuries of philosophical thought and decades of neuroscience. Here's why this matters for cosmic origins. Some philosophers and physicists think consciousness might be fundamental to reality, not emergent from matter. What if consciousness is a basic feature of the universe, like mass or charge? What if it's woven into the fabric of reality itself? This is called panpsychism, and it's been taken seriously by thinkers from Spinoza to William James to contemporary philosophers like David Chalmers. The idea is that consciousness isn't something that magically appears when you arrange matter in the right way. It's there all along, in some form, at every level of reality. Electrons might have a tiny bit of consciousness. Atoms might have a bit more. Your brain, with its trillions of interconnected neurons, has a lot. Consciousness is a fundamental property that combines and complexifies as matter organizes into more complex structures. Now, I know what you're thinking. That sounds insane. Rocks aren't conscious. Atoms don't think. But panpsychists aren't claiming rocks have thoughts. They're claiming that whatever consciousness is at its most basic level, some proto-experiential quality, it's present in all matter. Our rich, complex human consciousness emerges when billions of these tiny conscious elements combine. Why does this matter for origins? Because if consciousness is fundamental, it might have been there at the beginning. Maybe consciousness isn't a late arrival in a cold, dead universe. Maybe it's been here all along. Maybe it's what the universe is made of. Some physicists and philosophers have gone even further. They propose that consciousness isn't just in the universe. Consciousness is the universe. The cosmos is one vast mind, and we are thoughts within that cosmic consciousness. Individual minds are like waves on an ocean, temporarily distinct but ultimately part of one unified consciousness. This sounds mystical, and in some traditions it is. This is basically what Hindu philosophy says with Brahman and Atman. But some serious thinkers argue for it on philosophical grounds. Here's the argument. We know consciousness exists because we experience it directly. It's the only thing we know with absolute certainty. But we don't know that matter exists independently of consciousness. All we know are our conscious experiences of what we interpret as matter. Maybe, they argue, consciousness is primary and matter is secondary. Matter is what consciousness looks like from the outside. The physical universe is the external appearance of cosmic mind. If that's true, asking what created the universe becomes asking what created consciousness. And maybe consciousness, like mathematical truth, exists necessarily. Maybe it couldn't not exist. Maybe the fact that anything exists is because existence itself is conscious experience. This connects to some interpretations of quantum mechanics. The observer effect in quantum mechanics, where measurement collapses the wave function, has always been weird. Who or what counts as an observer? Some interpretations say consciousness is required. A conscious observer collapses the wave function, creating definite reality from quantum possibility. If that's right, and this is controversial, then consciousness plays a fundamental role in creating reality. Maybe the Big Bang required a cosmic observer to collapse the universal wave function. Maybe God is that observer. Or maybe the universe itself is self-observing, a cosmic consciousness observing itself into existence. John Wheeler, one of the great physicists of the 20th century, proposed something called the participatory universe. In his view, observers aren't just passive witnesses to reality. We're participants in creating it. The universe needed observers to become real, but observers needed the universe to exist. It's a self-referential loop, the universe creating observers who create the universe. Wheeler even suggested that quantum measurements happening now might affect the past, collapsing wave functions that have been in superposition since the Big Bang. In this view, we're literally creating cosmic history through our observations, reaching back in time to make the universe real. This sounds like science fiction, but it's based on real physics. Experiments called delayed choice quantum erasers show that measurements can indeed affect the past in certain quantum systems. The philosophical implications are staggering. Now, the materialist counterargument is that consciousness is not fundamental, it's emergent. Arrange matter in the right way, specifically in brain-like patterns, and consciousness emerges. No mystery, no cosmic mind, just complex information processing that creates the illusion of subjective experience. But here's the problem: we have no idea how this emergence happens. We can explain brain function in great detail. We can map neurons, measure chemicals, track electrical signals. But none of that explains why there's something it's like to be a brain. The explanatory gap between physical processes and subjective experience remains unbridged. Some neuroscientists think we'll bridge that gap eventually with more research. Others think it's a category error, like trying to explain color using only equations about wavelengths. The territory of subjective experience might be fundamentally different from objective physical description. If consciousness can't be explained by physics, if it's truly something extra beyond matter and energy, then we need to expand our ontology. We need to admit that reality contains both physical stuff and mental stuff, and maybe they're both fundamental. And if mental stuff is fundamental, if consciousness is woven into the cosmos, then maybe consciousness explains creation. Maybe the universe exists because a cosmic mind wills it. Maybe we're thoughts in the mind of God. Maybe the universe is God's dream. Or maybe it's the other way around. Maybe many minds exist fundamentally, and they co-create reality through some process we don't understand. Maybe you and I and everyone else are fundamentally conscious beings, and the physical universe is a shared dream we're all having together. These sound like wild speculations, and they are. But they're taken seriously by serious thinkers because the hard problem of consciousness seems to resist any purely physical solution. And if consciousness is irreducible, if it can't be explained away, then it needs to be part of our fundamental picture of reality. And if it's part of the fundamental picture, it might be part of the origin story, too. Chapter 18: The Anthropic Principle and Why We're Here. Let's talk about one of the most controversial ideas in cosmology, the anthropic principle. And I'm warning you now, this is going to make some people angry, but it might also be the key to understanding why the universe exists. The basic idea is simple. The universe must have properties compatible with the existence of observers, because we're here observing it. If the universe wasn't life permitting, we wouldn't exist to ask questions about it. This is sometimes called the weak anthropic principle, and it's basically a tautology. Of course, we find ourselves in a universe we can exist in. Duh. But the strong anthropic principle goes further. The universe must have properties that make the emergence of observers necessary or at least highly probable. This is much more controversial because it seems to suggest the universe was designed or finely tuned for life. Here's why this matters. The fine-tuning of the universe is not subtle. It's extreme. Change the strength of gravity by 1 part in 10 to the power of 40, and stars can't form. Change the electromagnetic force slightly, and atoms become unstable. The cosmological constant is fine-tuned to 1 part in 10 to the power of 120. These aren't just big numbers, they're incomprehensibly large. To put it in perspective, the probability of the universe having life-permitting constants by pure chance is like shooting an arrow at the universe and hitting one specific atom. Actually, it's way more improbable than that. So how do we explain this? There are basically 4 options, and they all have profound implications. Option 1, pure luck. We won the cosmic lottery. The constants could have been anything, and by pure chance, they landed in the incredibly narrow range that permits life. This is possible, but it requires accepting that we're beneficiaries of the most ridiculously improbable coincidence in history. Option 2, physical necessity. Maybe the constants couldn't have been different. Maybe there's some deeper theory we haven't discovered yet that predicts these exact values. The fine-tuning would be an illusion. These are the only possible values. The problem with this is that we haven't found such a theory, and there's no obvious reason why these particular values should be necessary. Why is the electron mass exactly 0.000511 giga-electron volts? Is there a deep principle that requires this? We don't know of one. Option 3, the multiverse. There are countless universes with different constants, and we're in one of the rare life-permitting ones. The fine-tuning is explained by selection bias. We couldn't be anywhere else. This works, but it requires accepting an enormous ontological commitment: infinite, unobservable universes. You're explaining one universe by postulating infinite universes. That's a heavy price to pay. Option 4, design. The universe was intentionally created with these parameters by an intelligent designer who wanted life to exist. This is the theistic explanation, and it's simple and elegant. One designer explains all the fine-tuning, but it has problems too. Who designed the designer? Why did the designer want life? What are the designer's properties, and where did they come from? You're explaining one mystery by invoking a bigger mystery. Now, here's where the anthropic principle gets really interesting. Some physicists argue that we should expect to find ourselves in a universe that's barely life-permitting, not one that's optimal for life. Think about it this way. If there are many universes with different constants, life-permitting universes can be divided into those that are barely life-permitting and those that are very life-permitting. There should be way more universes in the barely life-permitting category because there's more parameter space there. So if we randomly select from life-permitting universes, we should probably end up in one that's barely suitable for life, not one that's great for life. This is testable, in a way. Is our universe barely life-permitting or optimized for life? The answer is complicated. In some ways, our universe seems barely life-permitting. The cosmological constant is extremely close to the boundary where galaxy formation becomes impossible. Any higher, and no galaxies; any lower, and the universe collapses. But in other ways, our universe seems quite hospitable. Earth is in the habitable zone of a stable star. We have a protective magnetic field. The moon stabilizes our axis. There's liquid water. These feel like more than the bare minimum. This has led to debates about whether the anthropic principle predicts we should expect typical or atypical conditions. Are we typical observers in a typical life-permitting universe? Or are we unusual observers in an unusual universe? The anthropic principle also connects to the doomsday argument, and this is going to mess with your head. The argument goes like this: if you're a random observer, you should expect to find yourself at a random point in human history. You're more likely to be among the middle of all humans who will ever live than among the first or last. But here's the problem. We seem to be quite early in human history. If humanity lasts millions of years and spreads across the galaxy, there will be trillions upon trillions of humans. The fact that we're among the first few 100 billion suggests that maybe we're not going to last that long. This predicts doom in the not-too-distant future, hence the name. Now, many philosophers think this argument is flawed, and there are technical objections involving reference classes and self-locating belief. But it shows how anthropic reasoning can lead to disturbing conclusions. The anthropic principle also raises questions about consciousness and observation. If observers are required for reality, as some quantum interpretations suggest, then the anthropic principle becomes even more fundamental. The universe needs to produce observers, not just for us to be here, but for reality itself to be real. In this view, the fine-tuning that produces observers isn't just a lucky break. It's a cosmic necessity. The universe has to be observer-generating because observers generate the universe. It's Wheeler's participatory universe again, a self-referential loop of existence. Some physicists hate the anthropic principle. They see it as giving up on finding deeper explanations. Instead of asking, why is the electron mass this value? We just say, because if it weren't, we wouldn't be here to ask. That feels like a cop-out, like we've stopped doing science and started doing philosophy. But others embrace it. They argue that the anthropic principle is a legitimate selection effect that we need to account for. Just like Darwinian evolution explains biological adaptation through selection, cosmic evolution might explain fine-tuning through observer selection. The anthropic principle might also help solve the Fermi paradox. If the universe is so big and old, where are all the aliens? One answer: maybe life-permitting conditions are much rarer than we think, and the anthropic principle misleads us into thinking they're common because we're selected to be in a rare, favorable situation. Or maybe we're early. If we're among the first civilizations in the universe, that would be surprising, but anthropically expected if we use certain reference classes. The point is, the anthropic principle is controversial but unavoidable. We are here. That's a fact that needs to be incorporated into our cosmological theories. Whether it points to design, multiverse, or something else, It's a constraint that any theory of origins needs to satisfy, and that constraint might be more powerful than we realize. Chapter 19: The Information Paradox and Reality's Code. All right, we need to talk about something that connects everything we've discussed: information. Because at the deepest level, the universe might not be made of matter or energy or even quantum fields. It might be made of information. And if that's true, it completely changes how we think about creation. Let me start with a mind-blowing fact. Every black hole has an entropy proportional to its surface area, not its volume. This is weird because entropy is supposed to measure the amount of information in a system. And you'd think information would be stored throughout the volume of something, not just on its surface. But physicist Jacob Bekenstein and Stephen Hawking showed that black holes store all their information on their event horizon, the two-dimensional surface. It's like a hologram, where a 2D surface encodes 3D information. This led to the holographic principle, the idea that our entire 3D universe might be encoded on a 2D boundary, infinitely far away. Think about that. Everything you see, everything you experience, every thought you've ever had, might be information encoded on a distant two-dimensional surface. You're a hologram. I'm a hologram. Reality is a projection from a lower dimensional boundary. This isn't just wild speculation. The holographic principle has become central to theoretical physics, especially in attempts to unify quantum mechanics and gravity. It suggests that space itself is emergent, not fundamental. At the deepest level, there's just information, and space emerges when that information is organized in certain ways. Now here's where this gets crazy for cosmic origins. If the universe is fundamentally information, then creating the universe means creating information. But information, unlike matter or energy, can come from nowhere. In classical physics, you can't create or destroy matter and energy, only transform them. But information can be created. Every time you make a choice, you create information. Every quantum measurement creates information by collapsing superposition into a definite state. Some physicists argue that the Big Bang was fundamentally an information-creating event. Before the Big Bang, there was zero information. No bits, no structure, no complexity. The Big Bang was the moment when information started existing, and everything else, matter, energy, space, time, emerged from that primordial information. But where did the first bit come from? Here's a wild idea from physicist John Wheeler. It from bit. He proposed that every physical thing, every it, derives from binary choices, from yes or no questions, from bits. The physical universe is made of answers to questions. In this view, reality is fundamentally participatory. The universe answers questions when observers ask them. Before observation, before the question is asked, there are only possibilities, quantum superpositions. Observation, asking the question, forces reality to give an answer, to commit to a specific outcome. If Wheeler is right, then the universe creates itself through observation. It's a self-excited circuit, bootstrapping itself into existence through quantum measurements that reach back to the beginning and make the past real. This connects to quantum information theory, which treats information as a physical quantity subject to physical laws. Quantum information can be entangled, can be in superposition, can behave in ways classical information never could. And some theorists think quantum information is what the universe is really made of. There's an equation called the Landauer principle that connects information to thermodynamics. Erasing one bit of information increases entropy by a specific amount. This means information is physical. It has energy. Deleting information produces heat. Your computer gets warm not just because of electrical resistance, but because it's constantly erasing bits, converting information into heat. If information is physical and entropy always increases, then the total information in the universe must be constantly increasing. We're creating new information all the time through quantum measurements, through choices, through the unfolding of events. The universe is an information-generating machine. But here's a paradox. If information is conserved in quantum mechanics, as it should be in a universe governed by reversible quantum laws, then information can never truly be destroyed. But black holes seem to destroy information by swallowing it forever. This is the black hole information paradox, and it's been one of the biggest unsolved problems in theoretical physics for decades. Recent work suggests that information isn't destroyed by black holes. It's encoded in subtle correlations in the Hawking radiation the black hole emits. The information is scrambled almost beyond recovery, but technically it's still there. The universe preserves information at all costs. If information is fundamental and conserved, this has profound implications for origins. All the information that exists now must have existed from the beginning, at least potentially. The Big Bang didn't create new information out of nothing. It revealed information that was already present in the initial quantum state. Or maybe information was literally zero at the beginning and has been increasing ever since, growing from 0 bits to the incomprehensible amount of information in the observable universe today. Every star, every planet, every particle adds information. The universe is becoming more complex, more structured, more information-rich over time. This connects back to entropy in an interesting way. Entropy measures missing information, uncertainty about a system's exact state. Low entropy means high information. You know a lot about the system. High entropy means low information. The system is random and unpredictable. The early universe was low entropy, highly ordered, highly informative. We knew a lot about its state because it was simple and uniform. As entropy increased, the universe became more complex and harder to predict, but also richer in structure and possibility. Some physicists think consciousness is fundamentally about information processing. A conscious mind is a system that processes information in specific ways, integrating it, creating models, generating predictions. If that's right, then consciousness could emerge wherever information is processed in the right patterns. This brings us back to the simulation hypothesis and the mathematical universe. If reality is information and information can be computed, then reality could be a computation. The universe could be a vast quantum computer running the program of physical law, and we're subroutines in that program. Or maybe the universe isn't computing anything. Maybe it just is computation. The distinction between the computation and what it computes might be illusory. The map is the territory. The code is the reality. If the universe is code, who wrote the code? Or did the code write itself? Can information self-organize from nothing into the complex, structured patterns we call physical laws and cosmic evolution? some computer scientists have shown that simple algorithms can produce incredibly complex behavior. Conway's game of life, for example, has just a few simple rules but can generate patterns of arbitrary complexity. Maybe the universe is like that. Simple rules at the bottom, infinite complexity emerging from their interaction. But this pushes the question back. Where do the rules come from? Who or what chose these particular rules instead of others? Is there a meta rule that generates rules? And where does that come from? We're back to the same infinite regress that plagues every explanation. But maybe that's okay. Maybe reality doesn't need an ultimate ground. Maybe it's turtles all the way down, or more accurately, information all the way down, with each level of information encoding and generating the level below it in an infinite hierarchy. Or maybe there's a basement level, a final ground, and it's pure information without any substrate. Information existing in itself, for itself, as itself. The ultimate reality is not matter or mind or God, but information. Bits without physical instantiation. Questions without askers, answers without questioners. This sounds mystical, but it's where some of the most rigorous physics and mathematics is pointing. The universe speaks in binary. It processes, it computes, it stores and retrieves and transforms information. That's not a metaphor. That's literally what the laws of physics describe. And if creation was an information event, if the Big Bang was the moment information first existed or first manifested in physical form, then understanding origins means understanding information itself. What it is, where it comes from, why it exists, how it creates reality. We're not there yet. We're not even close. But we're asking the right questions. And sometimes, asking the right question is the first step toward finding the answer. Chapter 20. Synthesis. Bringing it all together. Okay, we've covered an insane amount of ground. Your brain is probably exhausted. Mine is too. But before we wrap this up, we need to step back and look at the big picture. What have we learned? Where does this leave us? Let's start by acknowledging something important. Every explanation we've explored, from the Big Bang, to God, to the simulation hypothesis, to the multiverse, has serious strengths and serious weaknesses. There is no perfect answer, no theory that explains everything, solves all problems, and leaves no questions unanswered. The Big Bang Theory is our best scientific description of cosmic history, supported by multiple independent lines of evidence. But it doesn't explain the initial singularity, the cause of expansion, or the origin of the laws themselves. It's a phenomenal achievement of human intellect, but it's incomplete. Cyclical models avoid the problem of an absolute beginning, which is philosophically appealing. But they face the entropy problem and conflict with observations of accelerating expansion. They're elegant in theory, but troubled in practice. Quantum creation from nothing offers a naturalistic mechanism for spontaneous existence, but it requires pre-existing quantum laws, which undermines the claim that it's truly creating something from nothing. And the jump from quantum fluctuations to a persistent universe remains poorly explained. The multiverse explains fine-tuning without invoking design, which many scientists find compelling. But it requires believing in infinite, unobservable universes, which is a massive ontological commitment. And it might be fundamentally untestable, which raises questions about whether it's science or metaphysics. The simulation hypothesis is provocative and captures something about our increasingly digital reality. But it doesn't solve the origin problem, just pushes it back a level. And it makes few testable predictions, rendering it more philosophical speculation than scientific theory. The God hypothesis offers a simple, elegant explanation. One intelligent, powerful being created everything. It explains fine-tuning, the comprehensibility of the universe, the existence of consciousness. But it faces the problem of evil, the problem of divine hiddenness, and the question of God's own origin. And it requires accepting the supernatural, which conflicts with methodological naturalism. So where does this leave us? Are we supposed to just pick our favorite explanation based on personal preference or philosophical bias? I think we can do better than that. I think we can extract some genuine insights from this exploration, even if we can't definitively answer the ultimate question. First insight. The question of cosmic origins is at the boundary of science, philosophy, and theology. No single discipline can fully address it. Science can tell us about mechanisms and processes. Philosophy can analyze concepts and arguments. Theology can explore meaning and purpose. We need all three working together. Second insight. The fine-tuning of the universe is real and demands explanation. Whether that explanation is multiverse, design, or something else, we can't just dismiss the extraordinary improbability of life-permitting constants. This is one of the most important puzzles facing modern cosmology. Third insight. Consciousness is deeply mysterious and might be more fundamental than we thought. The hard problem of consciousness remains unsolved, and that opens the door to possibilities we shouldn't dismiss out of hand. Maybe consciousness is fundamental. Maybe it plays a role in creating reality. We don't know, but we should remain open. Fourth insight. Information seems to be central to understanding reality. Whether reality is made of information, emerges from information, or is described by information, the concept keeps appearing in our deepest theories. Understanding information might be key to understanding existence. Fifth insight. There might be limits to what we can know. Some questions might be beyond the reach of human cognition or scientific methodology. That's not defeatism, it's epistemic humility. Recognizing our limits doesn't mean we stop trying to push them, but it means we should be modest about claiming final answers. Sixth insight. Multiple explanatory frameworks might be complementary rather than contradictory. Maybe the universe can be described scientifically as a quantum fluctuation and theologically as divine creation without contradiction. Maybe these are different perspectives on the same reality, like wave and particle descriptions of light. Now, let me offer a synthesis, not as a final answer, but as a framework for thinking about this. The universe exists. That's the one certainty. Why it exists and how it came to exist are separate questions that might have different answers. The how question is primarily scientific. We can study cosmic history, test theories, make observations. The Big Bang gives us the how from 13.8 billion years ago to now. Theories like inflation, quantum cosmology, and string theory are attempts to push further back. These are legitimate scientific endeavors that will continue to make progress. The why question is primarily philosophical and theological. Why does anything exist rather than nothing? Why these laws rather than others? Why is the universe comprehensible? These questions go beyond empirical investigation into metaphysics, meaning, and purpose. science and philosophy shouldn't be opposed. They should inform each other. Scientific discoveries constrain philosophical speculation. Philosophical analysis clarifies scientific concepts. Together, they give us a richer understanding than either alone. Personal beliefs matter here, and that's okay. Your world view, whether naturalistic or theistic or something else, will influence which explanations you find compelling. That's not a bug. It's a feature of being human. We interpret evidence through frameworks shaped by experience, culture, reason, and intuition. But we should hold our beliefs humbly, recognizing that certainty about ultimate origins is premature. The history of science is littered with confident proclamations that later proved wrong. Let's not repeat that mistake. What I find most remarkable is that we can ask these questions at all. We're hairless apes on a small planet, and yet we've figured out that the universe is 13.8 billion years old, that it's expanding, that it's governed by quantum mechanics and relativity. We've detected gravitational waves, mapped the cosmic microwave background, calculated the age of the oldest stars. That's extraordinary. Whatever created the universe, if anything did, it created beings capable of understanding their own origins. That might be coincidence, or it might be profoundly significant. So where do I personally land? I think the truth is probably weirder than any of our current theories. I think we're missing something fundamental, some insight or framework that will make everything click into place the way Einstein's relativity made sense of gravity and space and time. Maybe that insight will come from quantum gravity finally being solved. Maybe it'll come from a philosophical breakthrough about consciousness or information. Maybe it'll come from a place we haven't even thought to look yet. But I'm optimistic. Not that we'll definitely find the answer, but that the search itself is worthwhile. Every generation pushes our understanding a little further. We know more now than we did a century ago. We'll know more a century from now than we do today. The journey matters as much as the destination. The questions we ask shape who we become. The mysteries we contemplate expand our minds and our sense of wonder. And ultimately, that might be the point. Not to have all the answers, but to keep asking, keep exploring, keep pushing against the boundaries of knowledge. To be the kind of beings who look at the universe and ask, where did all this come from? And then spend our lives trying to find out. That's a beautiful thing. That's what makes us human. That's what makes existence, however it came about, worth celebrating. And you, what do you think? Let me know your opinion in the comments.